Hello, welcome to another stream. How about that? Bet you didn't expect that yet again. Hello everyone, hello NerdDebate1, here Hots and Plots, Duran Dells, Oud9, I Good Duke, Mr. Bodka, Gillo, Ji Young, Orange 23, Masters by the way, Daniel 14-2, MCourse 94, Der Pandas, hello everyone, welcome Nitrix, hello Eskershe, welcome, Cool Wizard, Rotten Chauncey, hello. Really glad to see you all today, guys. So today, according to the schedule, we're supposed to be doing game development, but yesterday we were working on a pretty cool topic. Yesterday we were working on the Bézier curves, right? So, and we implemented very simple Bézier curves. You can find the source code here. But we implemented them in a very straightforward way, where you just sample the Bézier curve, right, you know, through like over some intervals, and just draw the points, and then I guess you're supposed to interpolate them and stuff like that, which is kind of boring and meh. I was thinking, how can you implement something like that but using Fragment shaders? And that's a very interesting question, and this is going to be the topic of our stream today. Yeah, so I'm not sure if I will be able to come up with a general algorithm that will allow us to render like Bézier curves in a fragment shader of any degree, but I think we can come up with something that will allow us to render Bézier curve with 3 control points, and maybe even 4 if we're lucky enough, right? It just depends on how much energy and patience I will have at the end of the stream. So yeah, that's pretty much the idea of today's stream. You can find the source code of the previous stream here, and we're gonna continue developing like upon the source code that we developed yesterday. So, and obviously this thing is gonna be like its own separate playlist. You'll be able to go back and watch the first episode of Bézier curves. By the way, you can do that on our VODs channel. You can subscribe me there, and yeah, you can find the previous episode there. Well, it's not there yet. It's gonna be the first episode of Bézier curves is going to be uploaded today after today's stream, because we upload them on the next day after the next day's stream, if that makes any sense. All right, so let's open Team Mucus and let's go to the Bézier curve source code. Right, so let's fetch the latest changes. And let's take a look. I didn't even do any cleanup, which is kind of funny, and I probably don't even need to rebuild anything. But I'm gonna rebuild everything just in case. It doesn't take that much time. So this is basically our application. You can put a couple of points, and what it does, it renders a Bézier curve for that specific point. As you can see, we don't really render the actual curve. We just only render the samples. If you add another point, now you have 3 control points for the Bézier curve, and as you can see, yeah, it's a straight up Bézier curve. You can add another point. Right now we have 4 control points, and this is actually exactly how it is done in graphical applications, in the graphical editors like Inkscape or any other vector editors. So we can compare that to, for example, Inkscape. Have you ever gone through the project early problems? I think I solved a couple of them. In the past I was doing quite extensively competitive programming, so project earlier is just yet another website with problem for competitive programming for me, so I don't find it any special, to be fair. Anyway, so this is how it's usually done in the graphical editors. As you can see, you actually have 4 control points here for the Bézier curve. Maybe we can even make it a little bit thicker so we can see it better. I clicked on fill and stroke. For some reason it takes like a couple of seconds to load up. I don't know why. So here's the stroke, we have that, and I can make it like very thick, just for you, boys and girls, just for you. And there we go. All right, so as you can see, there's 4 control points. First one, second one, third one, and the 4th one. So as you can see, you have like a 4 control points, and it's actually exactly the same as we have something like this, right? It works exactly the same. It's the same math, and I created the 5th one. So, but our application actually allows us to create as many as we want, as many control points as we want. We can have like this interesting curves and stuff, but usually it's kind of completely unnecessary because you can just chain smaller degree curves together and achieve pretty much the same result. So like having several degrees is just completely redundant. So yeah, that's basically what we've done. And to know how exactly it works, there is a pretty cool visual explanation that I linked into the source code. And you can find it in README. So here is the visual explanation. I don't know who made that visual explanation. I don't remember if there was any author, but essentially you have 4 control points, and these 4 control points, they form 3 segments, right? You basically interpolate a point inside of these 3 segments and you get 2 segments. You interpolate within these 2 segments, you get 1 segment, and you interpolate within 1 segment, you get the point that follows the Bézier curve. And if you animate the interpolation, this is how it usually looks like. You can clearly see how the Bézier curve is drawn. So this is how exactly we sample it, right? This is exactly how we sample it. So essentially we have a function that accepts this t, right? This accepts this t, and returns us the position, the point on the Bézier curve for that specific t. And what we do, we just iterate through the t, all right, get the points and render them. And this is why you can see like these samples, right? So these are the samples. This is us going through the Bézier curve. Nothing special. Yep. So, and this is actually very straightforward. Okay, so what's the deal with fragment shaders? What's the deal with fragment shaders? Well, fragment shaders are executed on GPU, not CPU, right? And GPUs, they have a completely different architecture from CPUs, from classical CPUs, and they work completely differently. Right, so let's actually open my paint and I'm gonna show you something. All right. So essentially in shaders, and specifically fragment shaders, like OpenGL enables us with having several kinds of shaders. You have vertex shaders, you have geometry shaders, you have fragment shaders, and fragment shaders are essentially the shaders for like specific pixels, specific fragments of the scene, right? So you can imagine, right? You can imagine this is a screen, right? And a fragment shader, right, in our case specifically, if we're talking about 2D stuff, is going to be a program that is executed only for one single pixel on the screen. So you can write a program that works on one specific pixel and nothing else. It cannot look into the neighbor pixels, it cannot do anything else. It works for one specific pixel, and furthermore, it doesn't even know for which pixel it works for. Well, technically it can, it usually has the coordinates of that pixel, but you cannot look at other pixels. And essentially, GPU consists of a shed ton of small processor units, and what it does, it takes your program for a single pixel and execute that program for all of the pixels in parallel simultaneously. That's what it does, and that's why it ends up so fast, right? It ends up so fast. So, and that requires a completely different style of development. So some things are easy to do on CPU, some things are easy to do on shaders, and vice versa. Some things are difficult to do on CPU but easy to do on shaders. So specifically here, what's the problem? So we cannot just iterate through the T, sample the Bézier curve and just plop them on the screen, because we don't have our arbitrary access to the points. We just don't have that access. To be able to do what we do right now, right, we need an arbitrary access to the scene, so we can just plop those things into that, but we cannot have that. We have an access to a single pixel at a time, So that's create a problem. How do you even like write a Bézier curve for something like that? Well, if we could, for a particular point, so essentially here is the Bézier curve. Like you have a Bézier curve that is parameterized by t, right? So, and then it gives you a point, a particular point, right? A particular point, x and y, right? Of x and y. Maybe it's not like a great way to represent that, but maybe we can say it's a vector, right? But here, like usually in our case, we iterate through t and get p and plot that p on the screen. In case of a fragment shaders, we know p, and we need to answer a question: does that p lie on a Bézier curve? So essentially we have to reverse this equation, right? We have to reverse this equation. And this is exactly what I want to try to do today. Okay, does it make sense so far? Does it make sense so far? So is it clear why it is difficult to do that in fragment shaders and it's easy to do in CPU? Okay, makes a lot of sense. All right. So I was thinking about how to like approach this problem off screen today, and actually not only today but also yesterday after the stream. And I think I came up with a solution for n. Let's actually make it a little bit brighter even. For n equals 3 when we have 3 control points. Maybe we can even have something for 4 of them, but it's going to be even more difficult. Right. So yeah, so we have n, and we also have some sort of a t, which is a parameter of our equation of our system, which has to be between 0 and 1, right? Because this is what we interpolate here. And let's take a look what we can do about that. I actually posted this entire math that I'm about to go through on Discord yesterday. So people who are on our Discord probably already saw something like that. But for people who are not on Discord, I'm gonna actually repeat it live on the stream. And also I think it's gonna be useful to document that because the vote is gonna be on YouTube at some point, so I think it's quite important for documentation reasons. All right, let's take a look at the Bézier curve with 3 control points. So let's draw these 3 control points. So here's the first control point, second one, and the third one. We're gonna call them P1, the first control point, P2, and P3. So the first thing that we do, we just connect them into the segments, right? And then let's imagine that we have some sort of a t, which could be like, you know, 0.3. So it will end up somewhere here on this segment, and it's going to end up somewhere here on this segment, right? And this is going to create a point 1, 2, right? So interpolation between P1 and P2, and point 2, 3, right? Which creates another segment, right? And you have to interpolate it again. And that will end up somewhere here, and this is the point 1, 2, 3, 1, 2, 3. And this is the point, this is the final point that follows the Bézier curve as you go through t, right? As you go through t. So we can basically write p 1, 2, 3 as a function of t. So it's like a parametric function which is parameterized by t. So, and what is it equal to? Well, it is equal to interpolation, right? It is equal to interpolation between P12 and P23, as you can see, right? So, so that means we have lerp, which is linear interpolation from P12, which by itself, each of these things are also parameterized by t. So we take t as a parameter here, and we pass it further as a parameter for the lower level function. So essentially we have like architecture of the functions, so layers. On the top layer you have function p1 to 3, and then we pass the calls down to p1 2 and to 3, and so on and so forth, and it's like recursively goes down, right? So the second point is going to be 2 3 and t. Let's put it like that, and we put a parameter here. So what is lerp? What is lerp? It's a linear interpolation. Let's actually put a definition of lerp somewhere here so we don't forget about it. Lerp accepts 3 arguments. It accepts a, b, and then let's call it t. And essentially what it does, right, so t is supposed to be, as we already mentioned, between 0 and 1. It basically will return you a value between a and b according to the t, right, because t is basically percentage of the path from a to b. So to achieve that, you basically do a plus b minus a. B minus a is essentially distance between a and b. You take the distance between a and b, then you apply this percentage and you add it back to a. So this is basically what linear interpolation is, and it's actually a very important function that we're going to use throughout the stream, right? So in P1 to 3, this specific function is basically linear interpolation between P1, 2, which is also parameterized by t, P to 3, and t itself, right? So we are basically moving from P1, 2 to P2, 3, but P1, 2 and P2, 3 are moving as well. They're moving too. That's kind of the point. That's why they're also parameterized. Right, so we're moving from one point to another one, and those points are moving as well. So it's a very like dynamic system. So yeah, it's kind of actually interesting. It's kind of interesting. All right, so here's P1 to 3, but we don't know what is P1, 2 and P2, 3, right? Let's define them. So P1, 2, also parameterized by t. And it's basically interpolation from P1 to P2. So it's going to be lerp from P1 to P2 to P2, haha, using t. There we go. So that's what it is. So P1, 2 of t is going to be just linear interpolation from P1 to P2, like moving like here. Okay, so, but what is P2, 3? What is P2, 3? It's pretty much the same thing. P2, 3 of t is going to be lerp 2, 3, 2, 3. There we go. So we know what is P1, 2. We know what is P2, 3. What if we actually put these values in here? You see what I mean? You see what I mean? So, and actually, since we also know the definition of lerp, right? So, since we also know the definition of lerp, we can, you know, expand it and maybe bring it to some sort of like a formula, to some sort of like equation that we can then solve for each individual pixel on the shader program. You see what I'm going for? So we only need to sort of bring P1 to 3t to a particular form where we can essentially just solve an equation. And yeah, once we will be able to just solve an equation for each individual fragment shader, we will be able to code Bézier curves in the fragment shaders. At least Bézier curves with the like 3 control points, and it should be extremely fast. Actually, it should be extremely fast. Okay, so let's go through an expansion of all of these expressions and see how it's gonna go. We might as well actually first do it like that. So Bézier curves. Oh, you mean they're gonna be fast? Yes, they in fact are gonna be fast. So here's the first thing. So we just have to replace this thing with this thing. Should we produce the form? There's gonna be lerp, not lerp, but lerp. It's actually pretty ugly lerp. So lerp from P1, P2, T. I don't really understand how my paint sometimes like does this thing. I have 3 strokes, but then I do Control Z, it removes all of them. All right. So, and this is gonna be lerp P3. Actually, it's gonna be P2, right? P2, P3, T, and then T. There we go. So we did basically, we just replaced these things with their full form. My pain. Yeah, my pain is interesting. So basically what it does, it takes your actions and collapses them into a single action. And then when you do Control Z, it basically controls the group of actions, which kind of makes sense when you're drawing, right? Because maybe you have a lot of like small strokes, but it sort of caters to very specific use cases. All right, I don't think we're gonna have too much space on the right here. So I think I'm gonna start expanding these things according to this definition on the next line. Let's actually put it on the next line. Right, so it's gonna be P1, 2, 3 of T, right? And it's definitely gonna be lerp, right? It's definitely gonna be lerp. And the first lerp, according to this formula, is gonna be the following. So instead of A, we're gonna have P1. Instead of B, we're gonna have P2, right? So that means that here we're gonna have P1 plus the distance between P1 and P2, P2 minus P1, and applied percentage. There we go. So this is the first like component of the lerp. So the first component, and the second component is lerp between P2 and P3, and it's going to be pretty straightforward as well. P2 plus the distance between P3 and P2, right? Multiplied by T, and then here's the third argument. There we go. So we expanded like inner lerps, right? We expanded inner lerps, and now we have to expand the outer lerp. So essentially, now, according to the definition of lerp, we have to treat this entire thing as A and this entire thing as B. So the expression becomes more and more hairy and more difficult, but at some point the complexity it will start to reduce. You know, as you more expand and find the patterns and reduce them, it will become more and more concise. And this is what I'm hoping for. This is essentially what I'm hoping for. Is everything okay, Jiang? By the way, hello, Jiang. I don't remember if I said hello to you, but hello. Expand. Checks out so far. Okay. So let's start. So at the beginning of lerp, we have A. So maybe I want to expand that even further. What if I expanded this thing? Nah, maybe it could be too dangerous. Okay, so here's first comes A, and A in our case P1 plus P2 minus P1 multiplied by T. So here it is. This is A. Then we have to do plus the difference between like A and B, basically B minus A. Right, so that means we have to do B. So here is the B, here's the B. We have to put it here. P2 plus P3, P2, T. There we go. This is B, right, according to the definition of lerp. So we have A plus B minus A multiplied by T. Cool. So, and I use different kind of curly braces, so it's easier to distinguish them. It's like in Racket, you know, Racket is a Lisp, by the way, right? So, yeah, it's a Lisp, and as you know, Lisps have a lot of parentheses, but Racket actually allows you to use different kinds of parentheses, and they do not semantically affect the language at all. So you just essentially use them to distinguish between different levels of parentheses as you want, and people quite often do similar things in math as well, right? If you have a lot of nested parentheses, you just use different kinds of parentheses to distinguish the levels, because otherwise it becomes unreadable. And yeah, so for a single component here, I'm using like square brackets. I think it's pretty convenient. So this thing is supposed to be B, and we have to subtract what? We have to subtract A, and A is this thing, P1 plus P2 minus P1 T t, and we close the parentheses. So this thing, we can even actually denote them. I think we can denote them, maybe even with different color, right? So we can distinguish them, right? This is just A, right? This is just A. This is B of the lerp. This is B of the lerp. And this is another A of the lerp, right? So when you break down the expression like that, it actually becomes pretty readable. So the problem with math, right? The problem with math is that sometimes the expression gets so hairy, it's difficult to, you know, understand them. But here it is. So we have A plus B minus A multiplied by T. So yeah, might as well actually grab this thing. And in our case, it's gonna be, oh my God, my pain. Okay, so this is T. There we go. There we go. And this is just a big ass lerp. That's what it is. It's simply a big ass lerp. Slurp. Cheers, by the way. Big ass lerp. And there's actually several levels here. And look, it's kind of interesting. So you have this T, right? This T. So here's the first T. And you multiply this like big expression that contains within it another T. So we definitely are going to have T squared. So we're starting to have a quadratic equation. You see? We're starting to have a quadratic equation, and it kind of makes sense, because if you take a look at Bézier curve with 3 control points, this is a fucking parabola. Yes, obviously you're gonna get a quadratic equation. If you try to expand that and like get deep into this thing, you straight up get a parabola, because yeah. And it's kind of interesting. So essentially, yeah, we're gonna end up solving a quadratic equation, but we need to know its specific form, right? AKA cubic and quadratic Bézier curves. Yeah. So let's actually go a little bit deeper. How about that? Let's go a little bit deeper. So with 4 control points, you're probably going to be solving the cubic equation and so on and so forth. I'm not sure how to solve the cubic equation, but I'm down to solve quadratic equation in a fragment shader. So once we get the math right, we can try to code all of these things. All right, so what we're gonna do, can we just expand this thing? I think it would be kind of useful to expand this entire stuff into something like P1. I kind of don't like that we have a completely different color. Yeah, so I have to constantly do something like this. So we have P1 plus T multiplied by P2 minus T multiplied by P1. Did it help anyone? I'm not sure if it helped anyone, but yeah. So let's expand even further, right? Let's expand even further. I'm not going to expand this whole thing at once. I'm going to start expanding this thing and this thing separately. And then on the next step, we're going to expand the whole thing, hopefully. I'm not even sure if I'm using like a correct verb, because I don't speak English. I learned math in a Russian-speaking school, so all of the terms that I'm using according to math are like Russian terms. And I'm not even sure if this is how you properly translate them, so I'm sure. Our math, yeah. So P2 plus, and we are basically trying to get rid of the parentheses, so we will multiply T by that, so it's going to be T multiplied by P3 minus T P2. So this one is a little bit interesting. So I want to expand simultaneously this parenthesis and also get rid of this parenthesis too. So this one is going to be minus P1, right? It's going to be minus P1, and then it also becomes minus here, which means it becomes minus T P2 plus P1. Did I fuck up anywhere? because it feels like we're just getting rid of these things. TPI at the end. Oh yeah. Okay. Yeah, last with T. Thank you so much. This is so cool. I really like doing math on the stream because people can backseat me and actually catch errors like that. Yeah. Thank you so much. So yeah, I forgot that this thing has to be, and it's really difficult to see here, but has to be like this. There we go. We expanded that even further. Can we get rid of anything? I don't think we can get rid of anything here. Which is kind of sad, but yeah, plus TP1. Thank you so much. All right, another one. All right, so I'm gonna just rewrite this part. Does anyone get any school university flashbacks? Because I certainly get, and it's kind of monk-ass. I wish I never actually studied any of this in school, so I would never develop any like negative associations with all of this stuff. Unfortunately, I already developed negative association with all of this stuff, and it's really difficult for me to go through this math. So yeah, but I know that I need to do that, so that's why I'm, you know, struggling. So essentially, schools are like, they're ruining people. I think they're like, how to say that? I forgot the word. Oh, I forgot the word. Whatever. They're traumatizing. Yeah, schools essentially traumatizing people. Yeah, I would have probably learned this shit by myself, right? I would have probably learned it by myself, but no, we need a school to actually make me hate this kind of stuff. Anyway, so essentially we need to go through all of these, you know, parts of the polynomial and multiply them by t. So should be pretty straightforward. It's going to be plus tp2 plus t squared p3. You see, we're starting to get squares. Minus t squared. Oh my god, it's so inconvenient. P2. PS Comsci, why are you saying that to me? Did you find any mistake in my reasoning, or are you just backseating? Okay, so minus t p1 minus t2 p2 plus t squared p1. There's some simplification. So you're saying that no, there's no mistake. Okay, so there's nothing important then. So I don't really care about simplification or better way of doing that. The only thing I care about is, did I make any mistake? If I didn't make any mistake, I don't care about better way to do that, whatever the fuck it's supposed to mean. Okay, so cool. So what's important, whether did I make a mistake or not? All right. Can we improve anything here? So there is TP1. So there is one TP1, right? TP1. TP2. This is this one and this one. So T squared P3. Okay. So I don't see any other t squared. So there's like this one, but there's like this t squared and this t squared, I suppose. And there's also, oh, okay. I think I see one. So I'm gonna remove this thing. So that. So this one. All right. Cool. I think I'm gonna start maybe going through non-squared ones. Yeah, I think it's cool. P1, and let's do something like this. It's gonna be T And let's start collecting all of these things that have t, just t, without any squares or anything like that. So let me see where we have t's. All right, this one, this one, this one. Where's another t? So here's another one, and I think that's it. All right, so let's actually start going through them. P2, minus, it's too thick, minus P1, right, plus P2 minus P1. Cool. I think we did it. Did I make any mistake? Did I make any mistake? Again, I don't care about better way to do that. Did I make any mistake here? Seems good. Okay, thank you. Thank you so much. Cool. So now we need to go to the squares. Here are the squares, here are the squares, here are the squares. Okay. Don't trust my math though. No, it's not about trusting or not trusting, it's about like having several eyeballs, right? So you need to do this kind of stuff with like as many eyeballs as possible, so we can catch as many like mistakes as possible. Alright, so P3, right? So this is going to be P3 minus P2 minus P2 minus P2 plus P1. Cool. All right, so we're getting somewhere. We're actually getting somewhere, and I really like that because here is like the first non-square one. Then we have a square. We can simplify this stuff even further, I think, right? Because we have repeating things here, and we definitely have repeating things here. It's actually pretty cool. Milton doesn't work on Linux. Does it work on Linux? Or you typed forehead because it doesn't work on Linux and that you're trying to debate me, right? Because I heard about it, but I'm not sure if it works on Linux. If you're gonna debate me and it doesn't work on Linux, you're banned. Download. It's free for, but if you find it available, okay. Release page on GitHub. Squarespace, what the fuck? Okay, you lost me. Cool. So let's actually try to simplify that even further. P1 plus it's kind of, is it really 2 here? It's kind of suspicious that we have P2 and P2 here. But maybe it's okay. I think it's okay. So it's gonna be T. Oh, okay. So we have 2 P2s and 2 P1s. So that means I can do something like 2T, right? 2T and P2 minus P1. There we go. Would you look at that? Would you look at that? That's actually pretty fucking epic, mate. Am I a mathematician already? Am I a mathematician? I think I'm already a mathematician. Holy fuck. Plus T squared P3 minus 2 P2 plus P1. All right, I think we actually simplified it as much as possible. So here's the first essentially unknown. Here's the second, well, I mean, it's, you know, square of the unknown. And this is straight up a quadratic equation. So yeah. Essentially, you can draw the Bézier curve with 3 control points, without any of the like recursive algorithms and shit like that. You can just use this formula right away and it will give you what you expect. And to be fair, you know what I want to do? I want to try to code this formula into our program and just confirm that it works and produces the the Bézier curve. All right, so let's actually verify that we didn't make any mistakes by actually writing code. Sounds good? Sounds good. So, and after that, we're going to continue and see if you know, we can apply it to the fragment shaders. So I want to actually save this entire stuff. Saving, hopefully. Okay, cool. Yeah, let's go back to the code. Back to the code. We did enough math. We satisfied our math itch. So we're gonna go back to code. But after some time, we'll have to go back to maths as well. Again, not as well, but again. And by the way, people keep complaining that schools are useless. You will never need knowing how to solve quadratic equations in your, you know, day-to-day life. And look at me. Look at me. I'm about to solve a quadratic equation right in this stream. But maths is useless, it's never needed in real life. That's the secret, chat. That's the secret. I don't have a real life. Anyway, so let's see. So our Bézier sampler, accepts endpoints, right? It accepts endpoints. But let's actually create our special Bézier sampler. Which accepts 3 points, right? And it's going to be vec2. Let's literally call them P1, P2, and P3, right? P1, P2, and P3. And we also will need to accept T, right? We also need to accept T, and we just need to code this formula there. It's pretty straightforward. I had to relearn linear algebra so many times, haha. Yes, exactly. So again, jokes aside, I do still think that, you know, teaching this kind of stuff in school is kind of like pointless, because yes, majority of people will never need that, and people who do need that will forget that and will be forced to relearn it yet again. What's the point? Like, let's actually give people like more useful skills. I don't know, for example, you know, gardening or something. I don't know. Because I think people for whom it is important, they will learn it anyway, especially in the era of the internet, right? In the era of the internet, people will just realize, okay, so I need to do this thing. They will go to Google and they will try to research how to do this thing, and, you know, just do it. Metallurgy. Yeah, metallurgy, another useful skill. You know, gardening, metallurgy, cooking. Anyway. So let's put this formula there. Shaving you, exactly. By the way, nobody ever taught me in my entire life how to shave my head. I had to go to Google. No, I didn't actually go to Google, but yeah, nobody warned me that it's gonna take me 3 hours. So yeah, I had to learn it hard way. But to be fair, I actually, you know, learned how to shave my head pretty efficiently. So now it takes like 15 minutes. So it's actually pretty fast, relatively. Maybe I can cut it down to 10 minutes and maybe then to 5 minutes. I'm still trying to get that, you know, world record. Speedrunning head shaving, percent to assisted head shaving. Yes, world record. It's actually hard, believe it or not, it's actually hard. But for me, going to a hairdresser is even harder. So that's why I'm choosing to do that. So, no damage run. Yeah. So let's go. Damn, it's so funny. So P1, we have to actually do like several sums here, which is not particularly convenient in my opinion. So maybe we're gonna introduce a function, a vector to add. Right, so here's the vector to add. How about vector 2 to add 3, which will accept 3 points, vec to B, vec to C, and it will just, you know, sum them up. Where are my variadic functions? Well, I mean, C does have variadic functions, but they're shit. Where are my non-shitty variadic functions in C? In C, not in C++. In C++, they're less shitty, but they're very syntactically noisy and they're weird, to be fair. Like, you have to recursively generate, like, instantiate functions with different arguments to iterate through the arguments. Like, what the fuck is that? If they're all vec2, you just need to pass a counter, I guess. But then I lose the static type check. So I will still be able to put accidentally a number there and it will compile, and at runtime it may even work, but it will work incorrectly. So it's really nah. Alright, let's implement all of that. So we already have vec to add, so we can just implement that in terms of this thing. So add, what the fuck is this autocompletion? Company is actually weird. Company is the autocompletion extension for Emacs, and sometimes it works, sometimes it doesn't, and sometimes it just like works out of nowhere, and it still cannot understand why. Like did it index something or something happened? Why did you decide to autocomplete this all of a sudden? Like I don't know. It's really strange. Vec to add is gonna be A, B, C. I don't know what Lisp is. Me neither. I think Lisp is one of those like weird languages or something. Your autocomplete is just broken. I see. Thank you. Cool. Okay, let's go back. So we need to do return vec to add 3. So in here we need to have these 3 components, right? And the first component is P1, as we can see, right? So here's the first component. Pretty straightforward. I have a Lisp. Does it bother you? Does it bother that you have a Lisp? All right. I also do have a little bit of Lisp when I speak Russian, but I mean, it's just like there are physiological reasons for that. And there's nothing. Well, I can fix that probably, but it's too late for me. So yeah, so this here's the first component that we're coding. Here's the second component. So the second component is basically P2 minus P1. Here is the P2 minus P1, and then we have to scale it. So it's going to be scaled by 2t. There we go. So this is what we essentially coded here. So this one is going to be 2t p. I can even do something like that. T minus p 1. There we go. Can I have like a dot in the middle? I don't remember how to do the dot, but I can just put it like that. All right. So and we need to have the third component. What the fuck? Epic Unicode certificate. Yeah, I'm using a compose key, and it's basically compose plus underscore plus number. This is how I do that. So it's pretty convenient. So 6, 9. So what's the third one? What's the third component here? It's gonna be t multiplied by p3 minus 2 p2 plus p1. There we go. Is there a repo where the code for the compose key? Yes, there's like a .files, I suppose. I don't know, but I mean compose key. Like you just map in X11. You just map one of your keys to a compose key, and that's it. And all these combinations, they work automatically. It's not like you define them. Well, you can also define them, but they're default combinations, right? So what I'm just using default combinations for the compose keys. I didn't define them. Somebody defined them for me. Who am I to define them? Am I right? So, all right. So this is gonna be, all right. So this one is interesting. So this is a sum of 3 elements. But one of them is actually negative. So we can basically multiply it by 2. I think this is what we can do. We can basically multiply by 2. Do 2 30 seconds time out stack to 60? I didn't think so, maybe. Well, we're about to find out. We're about to find out. Vec 2, add 3. And here are the 3 companies. The first one is going to be P3. The second one is going to be 2P2. So it's going to be 2 P1. Right. But here it's going to be slightly different. Might as well actually maybe move some of these things here. So P2 is going to be vec to scale, and we're scaling it by -2 multiplied by t. That's how we're going to be doing that. And I guess that's it. I guess that's pretty much it. So this one is that, this one is that, this one is that, and this one is going to be essentially -2 P2. Cool. Isn't that cool? I think it's pretty goddamn cool. So here's the whole formula. We just coded the whole formula. Nice. So let's see if it's going to compile or not. So this is a Bézier 3 sample. Bézier 3 sample. 134. Yeah, it shouldn't be. Thank you. Thank you so much. Yeah, it's basically scaling. Yeah, thank you so much. Yep. That's actually pretty cool to do math like on the stream, right? People actually catch this kind of errors. Nice. So now we need to try to use that. So we render Bézier markers, and I think I'm gonna create something like this. Render Bézier 3 markers. It's going to have the same interface, so it's easy for me to like drop replace this entire thing. And the way I'm gonna do that, if n is greater or equal than 3, that means I'm gonna render. So we render the markers. Yeah, we'll have to iterate through this entire thing like this. Through this entire thing, doing Bézier 3, and we'll have to provide 3 points here. It's going to be PS0, PS1, and PS2. So, yep. So essentially, we're using our sampler based on the, expansion of this formula that we come up with. And this is quite important to check. I think it's quite important to check if it works correctly. So we have unused parameters here, it doesn't matter, so we can just ignore all of that. Cool. So the reason why I have it all now, so if we have markers, I will now be able to just put 3 here, and maybe it would be nice to just change their color to indicate that the code got actually changed. All of that compiles, and let's try to run the program. It's gonna be 1, 2, 3. And we fucked up. We actually fucked up. So now it's just some sort of a line, and it works completely incorrectly. I wonder where exactly we did a mistake. Looks good to me, yeah. Missed 2 squared. Oh, that's actually a good point. Thank you, Zhiang. Oh, yeah, so thank you for the coffee. God damn, so this is why we don't have a parabola, because we missed 2 squared. God damn, bro. Aspera, thank you so much. Yeah. Bézier 3 sample, here it is. So where should we have that? Oh, okay, so that means after that I have to do to scale, right? Right, and I scale it like this. Right, it's gonna be t multiplied by t. Cool. Nice, 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 nice. Did it compile? It does in fact compile. So let me put my math somewhere here and let's try to work out. Look at that. It still works. So now we have like non-recursive way of drawing it, right? And this is just a single expression. This is just a single expression over these three elements. That's actually pretty cool. And I think it does work exactly as the original one. It's just, and technically it should be faster, right? It should be faster because we directly, like, we don't have any additional calls or anything like that. So that means we coded everything correctly. That's actually kind of amazing, not gonna lie. That's kind of amazing. Do we want 3 or 4 points? I want to go for 3 for now because I think it's easier to do that, right? So because 4 points will require solving cubic equation, and do I want to go into solving the cubic equation? I'm not sure if I want to go there. All right, so we're done. We haven't implemented the shader yet. We just tested that we did mathematical transformations correctly. That's the only thing we did. So we just confirmed, okay, these mathematical transformations are correct. But that's not enough. That's not enough. Let's actually rewrite it again, rewrite this entire thing again. Something like this. So P123 parameterized by T is going to be equal to this one. P1 plus 2T multiplied by distance between P1 and P2 plus T squared P3 minus 2 P2 plus 1. All right, what was the original question? His handwriting is... Sorry, like I can only type with the same font size. I'm stupid. Yeah, you can clearly see that. Yeah, it's kind of fun. So and then I'll have to actually zoom in. Anyways, because I want to constantly like see the whole thing. All right. So what was the original question? What was the original question? The original question was, knowing this value, can we answer whether that point lies on the Bézier curve with 3 control points? Well, so essentially we do know this value. We can move it on the right side, right? We can move it on the right side, basically subtracting from P1, and then we get a quadratic equation that we just simply have to solve. We just get the quadratic equation. But here's the thing. If you remember how to solve quadratic equations, right? Quadratic equations. Oh my god. Oh, here it is. So it has these coefficients like a, b, and c, and so on and so forth. And they're scalars. They are just regular numbers. In our case, P1, P2, P3 are vectors. They're pairs of numbers. These coefficients are not scalars. They're literally vectors. How would you solve that equation then? You can think of P1 to 3 as basically a vector of 2 parametric functions as well. So you can think of it this way. P1 to 3 of t is essentially a vector where you have x1 to 3 of t and y1 to 3 of t. So essentially here you have not one equation, but two equations, one for x and another one for y. Yes, essentially two equations, right? So you don't have one equation, it's two equations. And so you can think of it this way: P1 is equal x1, y1, so the first point is that. Then P2 is x2, y2, and P3 is x3, y3, right? So then you can basically define this like system of equations, 1, 2, 3, of t is going to be equal x1, right, plus 2t, x2 minus x1, x2 minus x1, and the rest of this thing, plus t squared, x3 minus 2x2 plus x1. And you repeat the same thing for y as well. y1, I'm just basically repeating the above equation, but with a y instead of x's. y2 minus y1 plus 2 squared, y3 minus 2y2 plus y1. There we go. So we have this sort of like a system of equations. All right. So essentially, we have a point. Great, all of the mathematicians starting to show up. Yeah, so imagine that we have a point. We know it's x and we know it's y, right? We know it's x and we know it's y. What can we do on the shader? We can move, we can start solving the x equation, right? We move x to the right side, solve the equation and find t. Then you can put that t into the y equation and get a new value and compare it with an expected y. Right. You can compare it with the expected y. And if the expected y is close enough, you can quite confidently say that yes, the point lies on the Bézier curve, and all of that is going to be O of 1. Straight up O of 1, and you can do that in a fragment shader for each individual shader. Is going to be super fucking fast. And furthermore, so you have this y23, which you already know, and you have this essentially y, let's put it like prime, which is how to explain that? How to explain that? So essentially, you can use the difference between expected y and the found y as some sort of a threshold to control the thickness of the line, right? You don't necessarily have to like expect the points line up exactly. You can introduce some sort of a threshold, and that will probably increase the thickness. It will create like an area around the Bézier curve, and maybe you can even make it fade out as it goes away from the curve to create some sort of anti-aliasing, or maybe some sort of like a glow or something like that. You know what I mean? So I think it's going to be actually kind of cool if we try to do that. So yeah. So here is the math. I basically explored that right before today's stream, and I think it's doable. So you can do that on a fragment shader. So if you want a 4 control point, which is basically majority of vector graphic applications use, you will probably have to use like solve a cubic equation. We may try to go into cubic equations if we have enough time after we implement the fragment shader and stuff like that. If we won't have enough time, well, whatever. So yeah, before going into implementing the fragment shader, I wanna check if this approach will work. Are you planning to explain the number of points from 4? Didn't I just say my plans about 4 points? I think I just literally said what I plan to do with 4 points. All right, so I want to test if this thing works. So how are we going to test if this thing works? Basically, I'm going to be handling the mouse motion event, and I'm going to capture the position of the mouse, and I'm going to try it on each mouse move. I'm going to try to solve that equation, and if the point is close enough, it will somehow visually indicate that you are on a Bézier curve, right? So I just want to first check on the CPU if this math is correct. Right, so this is what I do. I think it's quite important to first check the math, and then once we confirm that this math is still correct, we can go into implementing an OpenGL application, implementing the shader and trying to code that math into a shader. And also maybe, yeah, it's going to be pretty interesting because there's a bunch of parameters you can put into the shader to make the curve a little bit more interesting and stuff like that. So I'm really looking forward into that. But before we go and like implement all of that, I think we need to make a cup of tea. What do you guys think? What applications has the Bézier curves IRL or for the technical? Let me show you. Have you heard about Inkscape? So it's a vector editor. So you can do these kind of things in Inkscape. So you have this curve, right? And it has like these controllers. And guess how they implement this curve? Guess how they do that? It's literally a Bézier curve. Like seriously, it's a basically Bézier curve with 4 control points. So yeah, here's your application. It's literally used everywhere. Everywhere where you use like vector graphics. So I work with Illustrator. That's alright. So same as Illustrator. Like yeah, so every vector editor they use Bézier curves. Like they're everywhere. They're so cool, they're so convenient, I love them. Alright, so I'm gonna start making a cup of tea. Does anyone have any questions while I'm making a cup of tea? So feel free to ask me anything. Quake 3 has a... Will you grow mohawk? No, I probably won't. Show your shower? No. Does anyone have any interesting questions related to, like, you know, on topic? Maybe something related to Bézier curves or math or quadratic equations and stuff like that. You know. Can we do a code review for moon landing program? What do you mean by code review? What exactly do you expect? What exactly do you mean when you say code review? What do you expect from me? Is there a list of the emotes which are available in the chat? Yes, use your favorite client. For example, I use Chatterino. I click here and it gives me the full list of the emotes available on this channel. So yeah. Are you going to use this to introduce a grenade in something? No, I'm not going to use it for anything. I'm doing all of that for recreational purposes. How are we going to handle the 2 solutions of the quadratic? That's a good question. I have no idea. We'll find out. We'll find this out while actually verifying all of this. Right, so basically, I will see what solution is going to be the best here. Oh, it's actually pretty easy. So we have 2 solutions. You put first solution into Y, and if it's too far away, you use the second solution. I think that's going to be the best way to handle that. Does it make any sense? So, and also we know T has a limitation, by the way. T has a limitation. It has to be between 0 and 1. So one solution can be basically outside of that range, and we can instantly throw it away. So the first thing I'm gonna do, I'm gonna implement the mouse moving thingy, and this mouse moving thingy is gonna just show the solutions for T, just 2 of the solutions for T, and we're gonna look at the solutions and build up an intuition what's going on, and once we have this intuition, we can make some sort of decisions. I think you're gonna get 2 solutions when you have 2 y values for 1 x value. Probably, we'll see. This is exactly what I'm talking about. Like, first I want to implement the thing that solves this equation on every mouse move, and then we can take a look at the solutions and how they behave. So then we can build up an intuition and then, you know, make some sort of decisions. Does it make sense? All right, so I'm gonna go to the kitchen because I need to boil up some water, right, for my team. So while I'm in the kitchen, don't go anywhere, right? Don't go anywhere, or I will come to your house and eat your homework. So yeah, and nobody's gonna believe you. So yeah, don't go anywhere, it's gonna be super quick. Hello. She's Googling, by the way. No, I'm not Googling. Trust me. I am not a Googling. Alright. So what do we got? We have this Bézier curve stuff, and seems to be okie dokie a karaoke. So here's the 3 points, and cool. So we need a function that will do the solution. So how are we gonna even do that? Okay, so it's gonna be a function that will just perform side effects. So it will accept 3 points, these 3 points, vec2, p2 and p3. Right, and on top of that, it will also accept p, which is the position of the mouse, right? So, and we'll have to solve all of that. So also let's call it solve quad EQ. So solve quadratic equation, and what it's gonna do, it's basically gonna just print this entire thing, right? It's gonna just basically print this entire thing. Alrighty, so I guess we're gonna go back, right? And imagine that we have some sort of a p, right? So here's the p, and it's essentially x and y. So let's assume that x 1, 2, 3 of t is equal to x, right? Equal to x. We might as well actually call them, let's call them p0, 0, 0, 0. So that means that x0 is equal to this entire shit, right? So it's going to be x1 plus 2t, x2 minus x1 plus t squared, x3 minus 2 x2 plus x1. So essentially, it's actually pretty straightforward. Like you have like, so what's the usual form of the quadratic equation? Okay, let's actually write this as a proper quadratic equation. So it usually starts with x squared. In our case, it's t squared. X3 minus 2 x2 plus x1. Right. So this is the first part. The second one is going to be 2t x2 minus x1. Okay, so this is the second part, and the third part is going to be plus x1 minus x0, right? So this is like this the last c part, and all of that is equal to 0. So this is our quadratic equation. Finally, our quadratic equation. And x0 and y0 is essentially these things. So we have p1, p2, p3, and p0 is basically the position of the mouse. Are you doing quadratic or cubic curves? Well, let me see. I don't know. Quadratic one. So, does anyone remember how to solve quadratic equations? Looks like 3 to me. Yeah, my handwriting is shit, I know. It looks like 3. So, you know, does anyone remember like discriminant and shit? Yeah, there we go. So first we have to calculate discriminant. I don't know, looks linear to me. Yeah. What the fuck? Is that like a canon that you define discriminant like as this delta shit? Seriously? Of the equation and often denoted using D or uppercase. In our school, in my K-Comrade school, we used capital D, none of this Greek stuff. Yeah, so, but to be fair, Greek letter looks kind of cool, so maybe I'm gonna use it. Okay, I'm gonna just write it down here. So, I just realized that I don't know how to draw triangles. What am I, a GPU to know how to draw a triangle? I'm gonna use big D. Big D is way better than, you know, than other stuff. So B squared minus 4AC. Where is my... Okay. Minus 4AC. So in our case, B is this shit, right? And A is this and C is this. What GPU do you use? NVIDIA GeForce something, but I don't have a drivers for this thing, so I'm using the Intel GPU, this one. Right. So by the way, big D. To be fair, like when you have a... Oh my god. Refresh the page, chat. We're back. We're back. We're back. Refresh the page. Refresh the page. Yeah, we're back. Back. Champions. In a handwritten cursive in Russian, the Russian D looks like this anyway. So, yeah, it doesn't really matter. So, yeah. Like, actually, in Russia, nobody ever writes, like, in handwriting, D. Like, nobody does that. It's purely for typography or something. Like, nobody does that ever. So... anyway, so I need to go to the kitchen, and yeah, I'm gonna just, you know, put pour some water for my tea, and then I'm gonna get back. Right. Don't go anywhere. Don't go anywhere. I'll come to your house and write all of your texts using Cyrillic. That's right. What's up? Rewrite BST. Why? Out 9. It's their fetish. Ah. Okay, so let's continue. So we have that. If the discriminant is positive, then we have two distinct roots if it's blah blah blah. We can actually start with just computing the discriminant, right? So B, right? So B in our case is gonna be 2x2 minus x1, right? So this is gonna be that, and this is gonna be squared, if I understand correctly, of course. So then, minus 4, so this is A. Oh boy, it's gonna be x3 minus 2, x2 plus x1. Cool. So this is A, and C is x1 minus x0. So this is the discriminant. Do you really think Tsoding is so three-head? Yes, I do think so. Okay, so here is the discriminant, and let's for now just calculate it. So let's actually call it not just discriminant, right? Let's let's call it dx. Let's call it dx because it's related to x, right? Because it's related to x. So I think my tea is ready. Dx. Chat, calm down, calm down. Alrighty. So now we need to retype this entire formula in C. Does anyone know how to program in C? I haven't programmed in C for quite some time already, to be fair. All right. So it's gonna be pain in the ass, but I think I'll be able to do that. Float. Oh fuck. Float dx. So in here, what do we have? So I think I'm gonna start with like A, right? Where I have A, what's Tsoding? Okay, thank you, I suppose. To multiply P2x minus P1x, right? So this is A. No, this is not A. I'm a beggar. It's actually B. So this is B. So, and dx is B squared, right? Okay, so what about A? A is going to be P3x minus 2 multiplied by P2x plus P1x. So this is A. So that means it's going to be minus 4 multiplied by A. And then we're going to also have a C, right? C, and C is just essentially P1x minus P0x. And we just multiply it by C, and we can arrange that as ABC, and there we go, we have dx. Now, I think I'm gonna just print dx, just to see what it's equal to, right? And as we move our mouse, we're gonna constantly be solving this equation, right? And we're gonna be looking at the discriminant, right? Alrighty, so this is gonna be d. Can I do that, by the way? Can I cannot have like underscore x, unfortunately, but I'm gonna do it like that, right? Print dx. No, it's MongoTOS. We're not printing dx. I'm sorry. So now every time I'm doing mouse motion, right? Mouse motion. So here's the mouse position. Here's the mouse position, and if the PS count is greater or equal than 3, what am I essentially doing? I'm doing solve quadratic equation where I use PS0, PS1, and PS2, and as P0 I'm using the mouse position, right? And this entire thing will just constantly print the discriminant for this equation, hopefully. We'll see if it's gonna work. It does in fact compile, and let's take a look at what we have here. Okay, so we're gonna have 3 of these things. So this discriminant is extremely huge, look at that. But as I go closer, to be fair, it's just positive. It's just constantly positive. It doesn't give us much information, right? It just goes out there. Yeah. And at some point, yeah, it becomes negative somewhere here. And I suppose depending on like different shapes and shit like that, it's gonna be just completely fucking, yeah. Huh. Oh yeah, by the way. Oh shit. Huh. It's very interesting. Okay, so discriminant by itself, I think it doesn't tell us that much. Oh, by the way, did I make any mistakes so far? When did you shave your head? Long time ago, actually. When I was 5. Make it vertical line and... okay, so we didn't make any mistakes. cool. So now, if the discriminant is positive, that means we have two distinct roots. Solve quadratic equation. Okay, so if dx is positive, right? So we're gonna be doing that. I think I'm gonna... No. So, and what's gonna be the first... Oh, we'll have to do square root. Do fragment shaders support square roots? Do shaders at all support square roots? I think they do. GL, SL, SQRT. I think they should be able to support. Yeah, they do support that. Nice. Well, I mean, it would be really strange if they didn't support that. Right. It would be pretty shady GPU, not gonna lie. Pretty shady GPU. Also has D. What is Gen D type? So look, it's several dimensions, right? Returns the square root of x. AMD GPUs don't support square root. Really? That's really strange. Okay. So the first solution is going to be T1 is going to be essentially this divided by 2a. Luckily, we already calculated a, b, and c, so it's pretty convenient to do all of that. And then we do minus b plus square root of the dx. Right, and the other one is going to be basically the negative one, right? Basically the negative one. So we have T1 and T2. So the only solutions that we care about, chat. 2 should... Oh shit, yes, you're right. Thank you so much. Thank you so much. Cool. And also this entire thing has to be like this. Yeah, the only valid solutions in our case are going to be the ones that are between 0 and 1. dx can become negative though, can't square root that. Okay. So T1, T2, I'm sorry. By the way, we can actually make all of that constant. Trying my best here. Okay. I have nothing against that. I have nothing against that. Alright, so it seems to be compiling. Which mathematicians am I right? Yeah. I wish I was a mathematician, but I'm not. I'm not. Alright. Okay. Look at that. Huh. So, first solution is correct though. Right, first solution is correct. Look at that. The second one is usually useless. And at some point it stops. What the fuck? Why does it stop? I think I know what is going on. It's just SDL didn't update something. Didn't update its area. But yeah. Huh. Ah, it becomes negative. So it's an area where it becomes negative. I see. But that's why it stops. That's cool. In some cases, it probably can become equal to 0. Right. In that case, it is. To be fair, it doesn't really matter. So the only reason why we have this separate case when discriminant is equal 0 is that because you basically will have 2 equal roots. That's why it's kind of pointless. But in programming, we don't really usually care. So that means we can just do the following thing. Greater or equal. Right, greater or equal, so whatever. In case of the negative, right, I think we have to deal with the complex stuff, but I don't think we need complex solutions, right? I don't think we need complex solutions. So, and what's funny is that usually, like, do we ever have a situation when the first solution is not correct, but the second is? So that's actually a good question. Hello, Roos605. I would really ask you to speak English because it's an English-speaking stream, not Russian-speaking. Okay, so here's the correct one. Can we just invert this entire thing like slightly? I feel like it could be like that. Okay, so in this particular situation now... Oh yeah, you were right. You're not supposed... Look at that. Look at that. Isn't it cool? So essentially, yeah. So you have two correct solutions because you have two y's for one x. Nice. I like that. So we can just go through all of them, right? If one of them works. So the only thing we need to answer actually is yes or no. Does the point lie on the Bézier curve, or it doesn't? So yeah, so for that we don't really need that much of information to answer yes or no. Okay, so this is one solution, and as I already said, once we have t, right, once we have t, we can put that t into y. Also, what happens if p1 overlaps p3? What do you mean? So let me take a look at the math yet again. P1 overlaps P3, so this becomes 0. P1, not quite sure what you mean. Once we have T, Alright, so, okay, so I can make them overlap like slightly. It just kind of becomes 0, I mean. Especially if you put it there. Alright, I think the time has come to actually find y, right, expected y. Once you have one of the solutions, we can have something like y1, where we have to retype the whole equation, but for y, adding like t there. Right, it's gonna be... I'm just thinking, do I want to have a separate function for this entire stuff? I think having the entire function is kind of an overkill. So I'm gonna go like this: p1y plus 2 multiplied by t1, right? Multiplied by p2y minus p1y plus t1 multiplied by t1 multiplied by p3y minus 2p2y plus p1y. Okay, so I basically retyped this thing. And the question is it correct? Is it even correct? Alright, so let's now replace these things. With t2. There we go. Now we have y1 and y2, which is quite interesting. Because these are possible values of y. That whole looks like a function called to me. What whole? You are not on Chatterbait, I'm sorry. So y1, let's actually print all of that here. y2 f. y1, y2. Okay. And another interesting thing, so what we expect one of these y's to be very close to p0y, right? p0y. If one of these y's is very close to p0y, we can confidently say that yes, it does lie on a Bézier curve. We might as well actually just put it here. So p0 equal to f. It's going to be P0x and P0y. So yeah, so what we're looking for is that y for P0 has to be equal or really close to one of these y's, right? One of these y's. So yep, and it doesn't compile because A. Okay. Shut, are you ready? Oh shit, that's a lot of information. I think we need to reduce the size. Okay, so we are about to put the cursor on the curve. Okay, you can kind of see 273 is really close to 267, right? 273 is really close to 267, and that's an indication that we are in fact on the Bézier curve. So, and as you follow it, you kind of follow that as well. Right, and if you also do something like this, I really apologize if the encoding is shit right now. So it is big data. And this time, oh yeah, this time it's actually the second one. If you invert it, now it's the second one that is close to our y here. So yeah, here we go. Math works out. Math works out really well. So now we can come up with a function essentially that just answers is P0 on the Bézier curve, and all of that takes, as you can see, only O of 1. This is O of 1 amount of actions. It depends on how you calculate SQRT. So if you don't have a hardware support for that, it may actually be not O of 1. You can create the difference between estimated point and mouse cursor. Yeah. So to be fair, we just need to find the one. Oh, you get it now. Alright, solve equation. So is it gonna be distance to curve or something? Maybe. To be fair, I wanna actually do it the following way. We're gonna return a boolean, yes or no, and we're gonna accept the threshold. Right. We're gonna accept the threshold, and the way we're gonna do that is return. So if discriminant is less than 0, then right away, no, it is not, even close. So if the discriminant is positive or equal to 0, what we're essentially doing is P0y minus yy, so it's going to be absolute fubs, less than threshold, right? This is the first one, or the same thing, or the second one. That's it. That's the whole function. To be fair, like, this is the whole shader that we need to implement. If this works out, this is essentially the whole shader. So is P0 on the curve? John Blow style of naming. I was trying to sub you, but Twitch says about credit card. I don't have a credit card. I'm sorry. Why do you tell me that then? But I mean, okay, sure. Thank you for consideration. Thank you for consideration. Don't talk to me if you're not a sub. I'm just joking, of course. Nobody have to sub. My content is absolutely free for everyone, so I don't have a paywalls yet. So, okay, let's try to compile all of that. Okay, so we have that is P on the curve, and let's introduce some sort of a threshold. What's going to be the threshold? So let's define this threshold. And it's going to be like around 10, I think. So threshold. And I think I need to print that. Let's constantly print that value. And cool. Naizu. Yezu. Kawaii desu. Alright. Boom. 0. So all of that is 0. and now it's once. As I follow the Bézier curve, can you even see that? Let me actually do something like this. Yeah. Right, all of that is 0, then once. Holy shit. To be fair, we could make it a little bit more interesting. We can draw some sort of a probe that follows your cursor, and if you are on the Bézier curve, we can change its color. I think it's actually a pretty good way of indicating that we are on the Bézier curve. We are on a Bézier curve. Okay, go. Wait a second. Yeah, and this visual representation is going to be way better. But to do that, I need to have this probe like this. Bézier probe. So it's initially going to be 0, 0, 0. Right? It's going to be located on 0, 0. And every time we move, I also assign that probe mouse position. So here's the mouse position. So let's put this somewhere here. So it's going to be Bézier probe threshold. That's what it is. Threshold, Bézier probe threshold. And I need to move this entire code to rendering. So now we're going to decide that on a level of rendering. So here we render the markers. Yeah, so essentially we just render all of these things and we render the stuff between them. So after that, what I want to do, if we have enough of these, like 3, the color with which we're rendering, yeah, so it's going to be that, and that we're going to do a render marker, right, with the renderer. At which position? At which position? At the position of the Bézier probe, Bézier probe. So what are the other arguments of render marker? And the color. So what's going to be the color? We're going to use green color for now, right? Actually, if you are on the Bézier curve, it's going to be red. Otherwise, it's going to be something like blue, whatever. So, and this is going to be the indication of all of that. And it doesn't even compile because this is not a mouse probe, it has to be Bézier probe. Right, there we go. Is it going to Bézier probe threshold, please? Yes, there we go. Seems to be about right. And now you can do boom, boom, look. Aha. This is the problem. Right, you can clearly see that when you are... Right, everything's okay. But then it extends kind of further. It extends kind of further because we're not taking into account t being between 0 and 1. And this is why visual debugging is so important, because it was kind of difficult to caught that bug while logging. Well, it was possible, but this one is just easy. You can clearly see that there's something fishy, right? It just answers that we are on a curve, but we are actually like on the imaginary like continuation of the curve, if you know what I mean, right? So it's just imaginary continuation. This is something that we'll have to fix at some point, right? So this is something that we'll have to fix. Alright, so how we can fix that? It should be pretty straightforward, right? So essentially t, for which we're computing all of that, has to be between 0 and 1. And if it's not, this is like, it does not even qualify as a solution, right? It doesn't even qualify as a solution. So, and is p0. Right. So here we're testing the solution, but before we can test the solution, the one important criteria of that solution is that t1 is greater or equal than 0, so that's quite important. Then t is less or equal than 1, right? So, and once we satisfy these solutions, only then we can try to check for the threshold. All right, so, and it's actually t1, excuse me, t1. right here. And the same goes for the T2, 0, T2, it's actually T2, excuse me. One and like this. Can I just align them so they, yeah, I just wanted to see them aligned and stuff like that. I am an imaginary continuation, cool. Thank you for letting me know, I really appreciate that. Cool. So now, as you can see, even if we are on imaginary continuation, it does not detect as being on the curve. And now it does detect as being on the curve when you like that. You follow the curve, and when you're outside of the curve, you're not on the curve anymore. Look at that. That's actually pretty cool. So we can easily detect that we are on the curve and none of the continuation bullshit. Nice. So this is the whole shader. Seriously, the shader is gonna look like that. Basically, we need to make this work for each individual pixel on the GPU. Doesn't the Bézier curve have 4 control points? Well, here we're just using 3. That's like, how do I start answering this question? Bézier curve can have as many control points as you want. So let me show you. So my point is, your question is incorrect. Your question is incorrect. For example, you can have 2 control points, 3, 4, 5, 6, 7, 8, 9, 10, as many as you want, and this is still a Bézier curve. So, no, Bézier curve can have as many control points as you want. A more correct question would be, doesn't usually Bézier curve has 4 control points in a real-world application? That is a more correct question, and in that case I would say yes, and suggest you to watch the votes since the beginning where we had a discussion on why we're using 3 control points specifically. Does that make sense? Can I have 69 control points? Yes, I think you can. Actually, I think our threshold for amount of control points is, I think 256, yeah, 256. So you can have 256 control points, and obviously you can have 69 of them if you want. What is this golden section? It's your mom. So it's just a Bézier curve. Why do you prefer French fries curves? It's a very interesting question. Thank you for asking it. All right. So now, once we figured out the whole math, we need to start writing OpenGL application. So yeah, let's quickly do that. So I need to decide what I'm gonna use for shaders. What is the easiest thing to use for shaders? To be fair, I was thinking about using Bonzomatic, but I built it from source code and it literally didn't work on my machine for some reason. Well, I mean, it worked, but the controls were just fucked up for some reason. But using something like this will be actually super cool. It's just like having a local shader toy, which is fast and not scuffed, but it was scuffed anyway. So maybe we're gonna just build a simple OpenGL application that just loads the Fragment shader and stuff like that. Should be pretty straightforward. I think we've done that many times, so we might as well actually do it again just to, you know, ensure that we know how to work with OpenGL. Do I want to make this a part of the repo? Does anyone need any of these math calculations and stuff like that? Is it even useful for anyone? GLFW or SDL with OpenGL is probably the way to go. Yeah, we already use SDL, but the last time I used like OpenGL with SDL, it was kind of a pain in the ass, I'm not gonna lie. So I'm not sure how I'm gonna go about that. Just upload the file to Git for whoever wants to read it later. Yeah, because we're also gonna have the recording of the stream, so maybe people will come to the repo from the recording and then they would want to look at the math yet again. I'm gonna do that at some point. Should be latex file though. That's a cool idea actually. Holy fuck. You know, I was always kind of like sad that after the uni, after I graduated from uni, I never had an opportunity to use LaTeX. But maybe the time has come to start using them again. Using LaTeX, by the way, is so satisfying when you write in formulas. When you're not doing anything complex, you know, doing anything complex in LaTeX is a pain in the ass, but when you're doing just straightforward, just formulas, writing formulas is so goddamn fucking satisfying, especially when they render into something like this beautiful from a mathematical book, you know, like this is so fucking cool. I love it. I love the feeling of just rendering the mathematical formula and just admiring the formula and how cool it looks. It's just so fucking nice. But again, so doing something complex in LaTeX is a complete pain in the ass. Alright, so I forgot how to do OpenGL in SDL, so I'll have to try to recall that. One thing I remember is that you have to use like SDL OpenGL flag, maybe in the renderer or maybe in the window. I don't quite remember. There's so many LaTeX renderers now. I'm not sure what to use. Back in my days, I used TechLife, I think, but back then we didn't have websites that rendered LaTeX for you. These days, people just use these platforms where you don't have to install anything and just put LaTeX there and download PDF or something. So back in my days, we didn't have that. So yeah, we had to like actually install TechLife and shit. LaTeX is wonderful. I wish that next generation Markdown supports it. Yeah. Okay, SDL to OpenGL example. How do you do OpenGL with this? Is this C++? Yes. Simple SDL to OpenGL. I really like how the whole math works out, and I'm so, by the way, proud that I came up with this math myself. Like, I know maybe for people who do math on a daily basis, this is like nothing, but for me, who's not mathematicians, and I, to be quite frankly, was never good at math in school and uni, I'm kind of proud of actually coming up with this solution. Not gonna lie, I think it's cool. So, and yeah, a lot of you know, functional programming definitely helped to come up with all of that. So yeah, that's for sure. Okay, so we have window flags, and this is what you have to do. You have to use window SDL window OpenGL. But on top of that, you also have to do this thing, SDL OpenGL. All right, let's actually try to do all of this. I like the delicious could be over time. God damn it. Like, I mean, I can only write with a fixed size font, okay? So every time I zoom out, I just kind of increase this, you know, the size of the font. The size of the font stays the same relative to the size of my screen and relative to the zoom, okay? So essentially, if the letters become bigger, you have to just zoom out. So you can clearly see where you need to zoom in and where you need to zoom out. So, all right. So the size of the letter tells you the level of the zoom, and the level of the zoom is important because it ensures that you include the relative context. You see what I mean? Right? So yeah, the level of the zoom required to read this writing is encoded in the size of the letter. So this is intentional. This is not a bug. This is a feature. Okay, because without a particular zoom, you may miss some context, and you have to like actually read it like that. Yeah. So yeah, I came up with an excuse. So cool. So we also have to include. Imagine if source code was written this way and people argue the font size. Yeah. Okay, so we need to include SDL OpenGL.h, and also we need to include GL/GLH. This is art. Yes. Where's the second main? Here's the second main. So I'm gonna have a resizable window, but on top of that, I'm gonna enable SDL window OpenGL, right? And hopefully that will create OpenGL window. The next thing we need to do, we need to create OpenGL context. Okay, SDL GL context. GL context, just a context. So maybe I'm gonna just split the screen so it's a little bit easier for me to do this entire stuff, bro. Okay. What the fuck is going on? I forgot how to use computers, I'm sorry. SDL GL create context window. Okay. So we have full screens in chat, then we have this stuff, set full screen, we don't need that. Is that it? Really? Is that the entire thing? Okay, so let's organize the, don't I have to set the current context after I created it? I don't think I have to set it. I'm sure pretty straightforward. Okay, so I usually have something like quit, which is initially 0, and while not quit, we need to slurp the all of the events. Are these Béziers just going to be a demo program? How to tell you? So look at the description of the problem. So this is just for educational purposes. So I'm trying to understand the math behind Bézier curves, and basically the repo contains the artifacts of me learning about Bézier curves. Does it make any sense? It's the end result is not going to be practical or useful for anything. The result is essentially artifacts of me learning, right? So some notes, some code snippets, things that you can maybe explore, and of course the recording of this the stream as well. The created content is active. Oh, I don't have to do that myself. Okay, thank you. All right, so SDL events. All right. It's great how you teach and learn at the same time. Yeah, I guess. I don't know, probably. It's kind of funny, there's like this saying that teachers in a particular area are essentially people who fail their career in that area. And people say that I'm a great programming teacher. Anyway, so too fucking true. Oh, Jiang is back. Welcome back. Why are you still in part 1? Well, because I failed my programming career. That's why. Anyway. So, alright, so it's going to be switch event type, and the only thing we're looking for is SDL quit. So once we receive the SDL quit event, we're done for. We quit. Then we have to set the viewport. The viewport is going to be 00 screen width, screen height, right? So GL clear color. Oh shit, we already have a background color though. Look at that. We already have a background color, but it's in hex. It's in hex. So what I'm thinking is that, can we do a similar trick with hex colors, but for OpenGL? That's a good question. Maybe eventually I'm going to try to do that. So right now I'm going to just fill everything with black, with void, and then I'm going to do GL clear, GL color buffer bit, right? And then we need to swap the buffers. What's up on the bot? Welcome to the stream. GL swap window. Do we have window? Yeah. Cool. So that should be working. That should be twerking. Did you just poke yourself? Go poke yourself. Alright, so we have a context and unused variable context. Okay, that's very interesting. And we have a redefinition of the main, so I'll have to actually make something like this. Alright, so yeah, we have unused thingy. And since we're not going to be using this context for everything, and SDL automatically sets the current context, maybe we're going to do something like this. Okay, cool. We also need to link with JL. So let's do the following thing. Let's introduce packages, and it's going to be a list of packages that we're using. So, and then I can do something like this. Packages. And is it gonna work? First try, it worked. So now we have an OpenGL application, a simple OpenGL application. Cool. And look at that. Look at that beauty. Cool. So now I can try to change the color of the background to confirm that it is in fact working. Right. And there we go. Here's the red color. So we have a actually proper OpenGL application. So do I need to reference this thing? I think I want to reference this thing because I used it while implementing all of that. So this is going to be in the references. What's up, Panapudi? Welcome to the stream. Find my imaginary roots. We are not actually doing any imaginary roots, unfortunately. I think we're just ignoring them. I think we're just ignoring all of the imaginary roots because they're not real. Okay, go. Now. So what's gonna be doing? What we're gonna do next? We need to start doing the shader stuff, right? And to be fair, I'm kind of tired of writing shaders in the string literals like this, where I would have like a vertex shader, right? And I'm gonna literally write them like this. So something like version 120. It's so dumb. I'm kind of tired of it. So let's actually implement like a runtime reading of the shaders. Yeah. So what was the last time I worked with the shaders? Yeah, to do all of that, we'll need to be able to slurp the file. Do we have any file slurpage? I think we don't have file slurpage. Let me steal some code. Did you ever try Rust lang? No, I've never tried it. I heard a lot about this language, but I never tried it. Is it worth trying, by the way? Is it a good language? Because I heard a lot of good things about that language. Maybe I should actually try it at some point. Okay. So let's find. Recently we implemented like a slurp function in BM, which is like virtual machine that we developed. Maybe I'm gonna steal some code from there. Maybe I'm gonna literally steal some code from there. Luckily, I released my virtual machine under MIT license, so I'm allowed to use the code from my own source code. So where did I have that? Let's actually search for slurp. I know that searching with Google, with GitHub search is actually kind of meh, but it is what it is. So what I'm thinking is neat. Yeah, let's actually steal this stuff. We'll have to adapt this thing. What this function does, it just reads the whole function into the memory. It also allocates the memory and stuff like that, and it just reads it into that. All right, so let's just copy paste it and try to adapt all of that. Cool. But we don't have a string view here, so we'll have to return. Let's return char star, right? Char star. And because we're going to be using null terminated strings, we need to allocate a +1 byte. Right? We need to allocate +1 byte. And after we read the whole thing, so where do we read the whole thing? It has to be something like fread. Okay, so here's fread. After that, the buffer has to be n. So this is how much we read. Oh shit. Oh yeah. So it's actually okay. N equal 0. So that creates the null terminated string. And the only thing we need to return here is just return the buffer. There we go. It's pretty straightforward. It just slurps the whole file into sister slurp file. So it basically indicates that we return C string, right? And C string is a null terminated string. Okay, so let's continue. So we're gonna have like a vertex shaders. So does anyone remember how to use vertex shaders, and what versions of the shaders do we even support? I don't remember. Vertex shader example. Yeah, so you have to provide the version. I don't remember which version do I support. So yeah, it's gonna be Bézier vert. It's a Bézier vert. Oh, and look at that, it automatically detects that it's a GLSL. Nice, I even have a highlighting for this thing. So I have to do version, I think it's 140 for me, I don't quite remember. So the runtime will tell me actually, so I don't have to worry about that. So void main, so here's the vertex shader. I don't think I need to return anything, so I'm just gonna be keeping it like this. So I need that just to test the file slurpage. That's the only reason why I need all of that. So how we're gonna do that? I'm gonna do printf s and sister slurp file, and we're gonna try to read Bézier vert, and let's see what's gonna happen. And it doesn't work because we need to also import error no. Otherwise it's not gonna work. Cool. And yeah, it actually slurped the whole file. You see, it slurped the whole file, so it was pretty straightforward. Wasn't it 320? I don't remember. I don't remember. Okay, so we need separate functions to compile shaders and shit. Did you finish your VM? No, I didn't finish it. For GL, the HPP, okay, so let's actually use that then. Okay. Compile shader file. We might as well actually like accept file path and just slurp the file inside of the shader file. Or maybe we can just do, you know, compile shader and accept the source code, source sister. And what that thing will return us, it will return, it depends. So the time has come for docs.gl. We need to get Sojing to RTX, an RTX GPU so he can finally use mesh shaders. Imagine one day I'm gonna start a stream and put in the title using mesh shaders, and it's not gonna be a debate. Like an actual stream where I learned how to use mesh shaders. All right. Okay. GL create shader. So we're gonna be using GL2. Where did my subscription? Wait, did you subscribe and I didn't notice that? How can I donate a game on stream? On Steam? I don't really play video games. I'm sorry. I didn't see your notification. It's not there. I'm sorry. But thank you if you subscribed. Thank you. Thank you so much. I really appreciate your support. Oh, Kashay is here. Hello. Welcome to the stream. We're doing OpenGL. And specifically, we're trying to draw Bézier curves in fragment shaders. So we're not doing the usual, you know, sampling the Bézier curve and then just interpolating the points. No. We're trying to draw that in the fragment shader, knowing only the current point, and we're trying to answer whether that point lies on the Bézier curve or not. So yeah, and we all kind of worked out the math, but we worked it out for the N3, for the control points, for the 3 control points. So which is kind of like an easy mode, but it still was kind of hard to figure it out. So right now we just we figured out the math, and now we coding it into the shader. So when I create the shader, right? When I create the shader, it gives me GLUint, right? It gives me GLUint, and that's exactly what we're going to return here. And on top of that, we need to accept the shader type. So let's accept GLInNum shader type. So that's what we're going to have here. All right, so so we have a Bézier vert, and I might as well actually copy Bézier frag, right? Bézier frag, and that's what we're gonna have here. Haha, very funny. Cooper and Sanchez. Okay, again. Once we created all of that, we're gonna have something like GLUint frag vert shader. We're gonna do compile shader. sister slurp file, Bézier. Why do you start on a new line after the function definition? Well, because I heard that if you write curly braces this way, you have a higher salary. So that's why I do that. So by doing it like that, you actually get more money. So it was actually statistically proven recently, and I really recommend to do this the same. This is actually my secret. This is actually my secret. So yeah. All right. So this is a Bézier, and this is going to be vert. And then we're going to do something like this. Is a vert shader, and it's going to be a frag shader. So, and let's take a look at the different types of the shader. So GL vertex shader and the fragment shader. So this is going to be GL vertex shader, and this one is going to be GL fragment. Yeah, fragment shader. It's Vulkan with fragment. Why not? It actually sounds very interesting, right? So I saw your links upon the So you posted like the interesting project where people somebody wrote bindings for Vulkan and Fragment. I don't know when I'm gonna try that, so but I'm considering it. How much do you get paid if you just don't write braces? It's a good question. Let me. Python AI engineer salary. This much. If you don't write any braces. It's pretty good, not gonna lie. Maybe I should stop writing braces as well. Alright, fragment shader. What's up, Everx? Welcome to the streamers. How are you fucking doing? So on top of that, once you actually compiled all of your shaders, you have to link them, right? So let's do GLUint link program, right? And we're gonna accept just two shaders here. GLUint vertex shader. It's gonna be vert shader. GLUint frag shader. And do we need anything else? I didn't think we need anything else. A happy new year to you too, Everx. Thank you so much. Yeah, yes. So we're gonna do assert. So compile shader to do, right? And we're also gonna have something like link program to do. Cool. So after we compiled all of the shaders, right? So what we need to do here, we just need to link the program. Link program vert shader frag shader. Cool. So once we linked all of that, linked GL use program, right? I think that's what we have to do here, if I remember correctly. Oh my god, this website is poo-poo. It's poo-poo. Yeah, you do GL use program. There we go. GL use a program, and we just use this thing, right? And now, what we'll need to do, we'll need to like draw 4 points for the quad. We're gonna be generating quad in the vertex shader, right? So I'm gonna just generate a quad for the whole screen, and then that quad will be passed to the fragment shader, and where we're gonna go through each individual fragment of that quad, and we're gonna simply, you know, draw a Bézier curve there. On top of that, like, we need to pass the 3 points, the control points, to the shader somehow. And luckily, 3 points is actually pretty small, so we can just use like uniforms to pass these 3 points. We can have like a uniform vec2 p1 to 3, and on top of that, I think p0. We don't need p0 because p0 is going to be the coordinates of the of the fragment, right? It's going to be GL frag chord or something. So this is going to be p0 in our particular situation, right? Yep. So I think this is how it's going to be. And then we're going to bind all of this uniform, and we also need to be able to control them somehow. Okay. Uniform vec. I'm not sure if my OpenGL or GLSL supports uniform arrays. So, I'm actually using very old GLSL, like it doesn't support a lot of useful things. We're about to find out. We don't even have a working program yet. Nitrix Life. I know that you're very excited because we're doing a topic you're familiar with. I do understand that. But let's implement everything incrementally, by small steps, okay? Let's not let our excitement to ruin the process of development and education, okay? So, let's not rush it. It's not a B. Yeah, why my program is not finished? Yeah, it's a classic question. So what we need to do after that, we need to do GL draw array, if I remember correctly. Draw arrays. Rush B keyboard. I'm a little bit hungry, to be fair. Just finish your program. Just finish your program. Okay, first specifies the starting index at enabled index. So I think we'll need this thing. Yeah, we'll need this function, and we're going to be generating a quad on the vertex shader using gray code, because that's the easiest thing to do, actually. Yep, so what's going to be the mode? It's going to be GL quads. I know that GL quads is kind of obsolete, but for our case, it can be the easiest thing to do. Yeah. GL quads. So it's gonna, the index is gonna start at 0, and we need to draw 4 of them. Right, we need to draw 4 of them, and I think that's gonna be essentially it. And let's try to compile all of that. Okay. So we don't have assert. Implicit declaration. So that means I need to include this. Well, GL2 is also obsolete, but what can you do? Classic, am I right? Zozin, why are you not using Vulkan? I swear to God, like every time I'm doing OpenGL stream, like there's at least one person who asks this question. Why are you using OpenGL? It's obsolete. Jump on that Vulkan trend. You guys are so predictable. Holy shit. Okay. So what I was doing, I forgot what I was doing. Yeah, I think I need to do this GL proto something, right? You know what I mean? GL proto ext. Wait. Yeah, GL ext something like this shit. Because some of these things. Oh my god, how can I make it copy pastable? Okay, there we go. So I need to do that right before all this shite, and I don't remember what I have to do there. So unused parameters, and this is still implicit. I think I have to make it 2. Okay. I keep forgetting what I have to set it to. Does anyone remember? Is it 1? Digimin GL histogram. So does anyone remember? Is it just that? Probably not. Oh, okay, it was actually like this. So maybe I don't even need this thing here. Yeah, I don't even need this, because if I import SDL OpenGL, it will just automatically work. Cool. So, and I just have unused variables warnings, but that's nothing, you know, nothing special. So if I try to run this entire thing, yeah, so we're trying to compile a shader, and yeah, this is not how you do that. This is not how you do that. Alright, so I think I want to make a cup of tea before we continue implementing compile, shader, and link program. Does anyone have any questions while I'm preparing my tea? Does anyone have any questions? Maybe somebody has a question like, what kind of tea do you drink? You know, the most frequently asked question. Or anything else, maybe something about OpenGL, or maybe something about Bézier curves, or like anything. Are we live? Yeah, I think we're live. What kind of water do you use? The wet one. Why are you not using Vulkan? I'm pretty sure it's not supported on my machine. The last time I tried to do something with Vulkan, the answer for my computer was something along the lines, buy a better computer or something. I don't remember what it was specifically, but it was something like along the lines, like you throw away your laptop and buy something new already. Stop wasting your life. Do you work with shape recognition? I don't know what that means, but I don't know. I recognized some shape in the past. What kind of coding are you? I don't know. The programming one. Mesa has a software implementation for Vulkan. Cool. I'm pretty sure it's a huge pain in the ass to set up, as anything on Linux. I wish there was something that is easy to set up. But after watching some Vulkan related streams from Provat, I realized that Vulkan is intentionally not easy to set up. Will your game use the new GPU curves? No. As already mentioned several times, I'm doing that for educational and recreational purposes. It's not related to any of my projects, it's just I wanted to look into that for a long time. I'm not going to be using it anywhere on my projects in the near future. Maybe in the far future I'll find a use for them, but no. Of whose stream did you watch about Vulkan? I already mentioned that. I don't know how you listen. But this view supports OpenGL 4, yeah. Oh yeah, it does support, like it's just like it needs to be set up properly or something, I don't fucking know. Does anyone have any other questions while I'm making a cup of tea, chat? So you can ask me anything. What about Metal? Well, as far as I know, Metal works only on macOS and I don't really have a macOS. What's the main idea? Learn how to do Bézier curves and try to render them using Fragment shaders. Calculate a lot of Bézier points in vertex shader? No. Or directly calculate Bézier pixels perfectly inside the Fragment shader without impellation? Yes. The second one, exactly. So I assume that you just joined because at the beginning of the stream I explained that, and for 2 hours we were figuring out the math how to do that for 3 control points, and we actually did it. So basically you end up solving a quadratic equation, and it's actually pretty straightforward. So what we're trying to do now, we're trying to write a program that implements that idea. And once we have this program, we can try to figure out how to do that with 4 control points. And so far, looking at the math, 4 control points will require solving cubic equation, which is doable, but probably going to be more complex. More than 4 control points is absolute pain in the ass and probably not worth even doing on Fragment shaders. So yeah. And by the way, of course, like the recording of the stream is going to be available on YouTube. So you can actually subscribe to this YouTube channel and watch since the beginning of the stream, where we actually discussed all of that, where we were figuring out the math and stuff like that. You actually missed a lot of interesting stuff. So right now we're just like, we figured out everything, we're just implementing it and see if it's gonna work or not. All right, so I'm gonna go to the kitchen because I need to boil up some water. Don't go anywhere. Or, you know, permaban. Mod. Ban everyone who left the stream. Permaban. What about curve width? Will it be shader parameter? Yes. We even know how to do that. Yes. So actually math works out so well that you can even have some sort of like a distance between like the curve and your current point. So you can actually use it as a threshold to control the width and stuff like that. All right, so let's continue. Hello. I'm back. Too back. Alrighty. Oh, by the way, speaking about the math, so here's the math. Is P0... Wait a second, did I? Oh shit. Oh, God damn it. I actually stashed my changes with the math. So, but the math is this. This is the whole math that you need to figure out whether a particular point is on the Bézier curve or not. So it's pretty small. It's pretty small. I think I did a fucky wacky chat and a little bit of oopsie doopsie. Mathematician sorting transformed into programming sorting in the background. Yes. I mean, why do we even have to like separate these two activities? I think they're closely related to each other anyway. So, math is programming, and programming is math. Fight me. All right. So let's actually compile the shaders. First thing we need to do to compile the shader, we need to create the shader, right? We need to think like a shader. We need to be the shader. All right. Okay. GL create shader. This is how we gonna do that. So we just call this function. You see how easy it is? It's super fucking easy. You know, can your Vulkan do that? Is creating a shader in Vulkan as easy as just calling a single function? A single function with a single parameter not being a huge structure that you have to fill up for half of an hour. Can your Vulkan do that? I don't think so. All right, after we created the shader, right? Oh, we have the whole example here. So you create it, then you do a shader source. Essentially, you associate your source code with the shader, and then you compile it, just like that. GL shader source, right? GL shader source, and here's the shader. It contains only one line, and here is the source code, right? It has to be like this, and we are not passing any sizes of this source code, so we can put a null here. What about bounding box or bounding polygon for fragment shaders to fill? Do you calculate it also, or just fill whole screen? I don't know what you mean. We just have a quad, and we are drawing like it in the inside of the texture of the quad. That just, I don't know. All right. So, and then we need to compile the shader, right? We need to compile the shader. Here we go. So here's gonna be the shader. So after that, we need to query the compilation status of the shader because it may not compile. And let's be honest. In 98% of the cases, your shader is not gonna compile because it's a, you know, real world, and you don't know shaders. So, so we need to do something like gl int compiled. What's up, Lamburak? Okay, I think the time has come to time someone out. I think 10 minutes should be okay. All right. So some people just want a little bit of attention, just a little bit of attention. I guess we can afford giving them this attention. Sure, I'm in a good mood today. Why not? GL get shader IV, right? And here is the shader, right? GL compile status. God damn it, Outnet. Compile status. No, here stop. Chat, stop making me giggly. Holy shit. Okay. All right. If we couldn't compile the vertex, not equal GL true, we have to say, oh, we mates didn't compile. So, yeah, first we'll have to allocate. Allocate a buffer where we're gonna keep all of that. So we have message It's kind of interesting that the buffer itself called message, but the size of that buffer is called log length. So maybe it would make sense to call this thing log and this thing log length. I don't know. But to be fair, my tea is ready. So I'm gonna go to the kitchen, pour myself some hot water. Don't go anywhere, or again, you're gonna be banned. Just like the dude who got timed out, you know, a minute ago. Just like that. Don't go anywhere. Don't go. What? 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 Ah, the fuck. All right, we've got the tea. We've got the tea. Alrighty. So, what do we got? We need to allocate some stuff. So it's gonna be GL char. And we're gonna call it log, and it's gonna be like 1 kilobyte. 1 kilobyte of the buffer should be enough for everyone. And then we're gonna allocate a variable for the size of this thing. We're gonna call it log size. There we go. So, and then we have to call the get shader info. Get shader info. And this is how we're gonna call it. So the shader is going to be the shader. Max length is going to be the size of the buffer, so it's going to be size of log. And then we're going to provide the pointer where we're going to store the size of this entire thing. And then the buffer itself. Wait a second. Don't you have to like... No, you don't have to do anything. Okay, so we just extract the log and stuff. And that should be enough. That should be enough. Afterwards, we should just be able to print this entire thing. Write the error to the log. Okay. What is that? Which T99 on the bottom? Is it real? Yes, it is real. Everything on this stream is real. Even me. Some people don't believe me that I'm real, but I am in fact real. I'm in fact real. Alright, so let me see. Shader compilation failed. So, and speaking of whether I should pass the file path here or not. Well, I kind of want to have a file path when the shader compilation fails. So I think I'm gonna actually change it to file path, and we're gonna try to compile shader file, right? We're gonna try to compile shader file, and here we're gonna have char source sister, and it's gonna be sister slurp file, and we're gonna just have a file path. There we go. Here it is. How can I become like you in coding? Why do you need to become like me? Like, you're not me. Just be yourself. So, yeah. Don't try to become like me. Maybe if you just be yourself, you're gonna be better than me. Who knows? I'm not you, what the fuck? Yeah, I know. It's hard to believe, but it is what it is. Shader failed to compile, and we're gonna provide the you know, the name of the shader. So the name of the file name of the shader, and here we're gonna have something like this. And of course this is gonna be a new line, and we might as well actually use std error, and it's going to be log size, and then just log, and after that we'll have to exit with 1, indicating that we did a fucky wucky oopsie doopsie. That should be it, actually. This is the whole thing. This is how we compile the shaders, believe it or not. And then we can just return the shaders that we just compiled. Furthermore, maybe after we're done compiling the shaders, it makes sense to free the source code, right? So because we don't use it anymore, so we allocated it and then we just freed. Yeah. So sounds good. Sounds good. Does it compile? It doesn't even compile because it's supposed to be what? Passing argument 3 of shader from incompatible pointer. Oh fuck! Why is that an incompatible pointer? Excuse me, do I have to do it just like this? Expected const GL char const, but got. Huh. What? Has to be GL char. Okay. Okay, let's take a look. So you have source code, GL source code. Here it is. So it has to be just GL char. It has to be just GL char, and there's something really weird going on. Expected const. Do I have to make it const? Excuse me. Why does it have to be const? Can you just move it? What did I miss? Okay, it's just a warning. Let's actually take a look at the actual errors. All right. So compile shader. So you're missing layer of const. I don't understand why is that a thing, but okay. All right. So this is gonna be like this. Cool. All right, I don't quite understand why this is important, and it's still not enough, because expected const char const, but argument is of const char const. Okay, so now if I try to do something like this, you will be happy? Why is that a thing? Why can't I take a mutable thing and turn it into immutable? So maybe maybe this is what needs to be. This is so weird. Okay, so it does have to be like that. Ah, because I'm pointing at this thing. And it's better be not modifiable pointer to not modifiable memory. I see. Oh, that's complicated. I see. Because we're pointing to this thing and it requires very specific access for the pointer to which pointing and for the next level of indirection as well. So it requires this thing not being modified and on the next level of indirection also this thing not being modified. And we're pointing at that thing. Holy shit. Like it requires like, yeah, like not modifying at least 2 levels of indirection. Imagine not having borrow checker. I wouldn't expect that such a strict control from a C. Well, I mean, there's not that strict control anyway because it's just a warning, right? But yeah, it's kind of interesting. All right, so and then we free, and it kind of discards the const. Oh shit! So essentially, we have a buffer, right? And we can sort of, kind of do something like that, so we can then later free the buffer. Oh shit! Yeah. So, oh fuck. But it's kind of cool that it requires this thing because it sort of documents that, dude, I'm not gonna modify this variable, right? I'm gonna just look into it. So I think it's cool at the end. I think it's kind of cool. All right. So let's make a cup of tea. Oh, Zitimus. How is the sound, by the way? Am I still muted? It's fine. Cool. I suppose a timeout actually fixed the sound. Ah. Fixing sound with timeout. Chat, come on. It was me. Well, I'm really glad that you finally realized that. Yeah. I'm really glad that you realized that the problem was you. And I'm really happy that it's fixed now. So now you can enjoy the quality content. Alrighty, so this seems to be good, and let's try to run it. And yeah, so now it fails at link. We can try to do the following thing, where we can take the vertex and just put some shit here that will not compile and just run it. And as you can see, it says error syntax expected this, but we got some poo-poo instead. Cool. Furthermore, can I do some gut code remove and remove a space from here? Can we do something like that? I think it's actually a pretty good idea. And I'm gonna tell you why. Because now I can try to run the Bézier thing from here, and probably even... God damn it, it doesn't allow me to easily jump there, but... I wonder if... So it's +2. How about -2 +2? I'll have to recompile this entire thing. Oh shit, and it... I'm almost there, chat. I'm almost there. I need to get rid of the backticks. Can you hear the dogs in the background? Why are you not working? Whatever. So it's not gonna work properly anyway. But Slav PLS? Yeah, a little bit of Slav PLS action going on, I suppose. Okay, so this is a pretty good error message. I can probably just go here and go to the 6th line and... Oh, apparently it numbers from 0, but yeah, that's okay. Okay, so now we actually can report errors and shit. Oh, the dogs are barking because somebody setting off the fireworks. Alright, makes sense. Alright, now the time has come to link the program, Chat, are you ready? Are you ready to link the program? So essentially we have to create the program. Yeah, it has to be like this. GL create the program. Oh, Jiang. For some reason I thought you were Nuffly because you use Nuffly emotes. Yeah, okay, you're not Nuffly. You're Jiang. Alright. So GL uint program. GL create program. And the only thing we need to do, we need to just attach the shaders. We don't need any attributes here, I think. Right? We're not gonna do any attributes. Zhuang and Nuffly are the same person, yes. Do we like dogs? I'm okay with them, I suppose, but I'm more of a cat person, right? So I like pretty much majority of the animals, but if it comes to actually having a pet, which I assume that's what you mean, I'm more of a cat person rather than a dog one. So yeah. Primarily because cats are assholes and I really like them because of that. So okay, let's do it like this. So we need to attach the shaders, attach shader, and we're gonna do program, and we're attaching the vertex shader, and then I like dogs more than cats. Yeah, understandable, fair enough. So that means we cannot be friends, Daniel42. I'm really sorry. It's just not possible. You're a dog person, I'm a cat person. Like, yeah, we have to be enemies. So, I'm joking. Yeah. All right, let's do GL link. GL link program. I'm an uwu person. What that means? What kind of animals do you keep as pets then, if you are an uwu person? I'm an asshole. Does that mean that you like me? Yeah, I guess. All right. So after we linked the program, we also need to retrieve its linkage information. There's a local bird that literally makes uwu. Is that the one that I think about? Probably. How do you call it? Asian coral. Oh shit. Do you have a video where it actually does the uwu sound? Oh shit, that looks cool. I really like the eye. Look at that eye. Holy fuck. It's a fucking epic eye. It's a red eye. This one is even better. So, okay, it's a female and this is a male. Cool. They both look cool actually, both male and female. Holy shit, they're so cool. I like them. Nice. Look, this is a badass looking bird. Alright. So we need to have something like GL int linked. Right, it's going to be like this. And then we'll have to query the linkage status. Right, the linkage status. So I'm not gonna copy paste the void anyway. Does Markov chain still recording our messages? It's not recording your messages, it's training based on your messages. It's not recording anything. The Markov chain itself. Other things maybe do, but the Markov chains no. Alright, GL link status. Okay, so this is a GL link status. I mean, we have a separate component that logs everything, but it's not a part of the Markov chain. The fuck is this message? Alright, if not linked, it actually has to be done like this. If it's not equal GL true, that's what we're talking about. If it's equal GL true, we have to do the similar thing. GL size, log size equals 0. Then we have GL char, which is log, and it's going to be 1 kilobyte. Can we afford in 2020 to allocate 1 kilobyte on the stack? I think we can. Alrighty, shut. So, and then we do GL program info. I wonder in which case we cannot link the programs. Probably when the output of the vertex shader doesn't match the input of the like fragment or something, or maybe they don't have enough attributes. I didn't really program in OpenGL enough to actually experience all of the problems of OpenGL, but you can imagine something like this. So, and also we have to do it like this. It's going to be pointer to the log size, and the log itself is going to be a log. And then we're going to just do fprintf. So what was there? Failed to link the shader program, and we can just print the error here. So it's going to be log size and then the log itself, and then we're going to just exit. This is not how you exit. That's how you exit, and then we can just return the program. Shazawaku-sama, hello, welcome to the streamers. How are you doing, my comrade? How are you doing? Alright. Good day after barbecue feels so good. Oh my god, I haven't had a barbecue for so fucking long because of the corona shit and stuff. Yeah. Actually, this summer sucked. Holy fuck. Because of the COVID and shit. What do you do in your free time? I cry. Alright, so let's continue. Oh, not the last year summer. I'm sorry. You're gonna be doing dad jokes now? Okay. So what happened? Passing one argument, this has to be std error. There we go. Cool. Yes, failed to link shader program error. The vertex shader does not write GL position. Look at that. Look at all of these epic linking errors. You remember how I was talking like that I never experienced the the linking error? There you go. Now I know how a linking error looks like. So what I essentially need to do in the vertex shader, I just need to set GL position to, I suppose, something like this. I think it will be just a vector of 4 of zeros and stuff. And there we go. That seems to be working. That seems to be twerking. Cool. Absolutely. Fucking epic, mate. Alrighty. So we have our boilerplate. And now, the thing we need to do, we need to generate the quad. Right, we need to generate the quad. Usually people do that by creating like vertex buffers and stuff like that. But here on the Zosian channel, we're generating the quad on which we're drawing in a vertex shader, right? You see, we're making a GL draw array call with 4 points, right? So that means our vertex shader is going to be called 4 times for each individual vertex given the GL vertex ID, right? So, and it's going to be from 0 to 3, 0, 1 to 3. And based on 0, 1 to 3, what we have to do, essentially, we have to generate a corresponding quad. So we can do that by using gray code. Gray code. So we already explored that several times, but the idea of the gray code is that it's a binary code where each consequent number in bit representation differs in 1 bit, right? So, and essentially, we have 4 numbers, right? That means we're using like 2 bits of indexing. So, and if we treat these bits as corresponding angles, as corresponding corners of the quad, we can actually generate a quad, like points of the quad in a clockwise or counterclockwise order by using just a gray code, right? Basic error correction. Yeah, you can also use it for basic error correction, but we're gonna use it for generating a quad. All right. So here is the vertex ID, and I wonder if I can just test if it's equal to anything, if it actually supported, because I don't remember if it's supported or not. So the shader seems to be compiling, which is good. Gray code giving me K math flashbacks. Okay, so let me go here and let me set the color of the background to black, so we can distinguish it from the quad. So here we go. Here's it's black. Now I'm gonna go to the fragment shader, and in the fragment shader I'm gonna set the GL frag color, if I remember correctly. I think this is how it's called. Is it? Wait a second. Why is it red? Huh. Why my mode actually shows that? Anyway, so I'm gonna do something like this. We're gonna make it like red, so you can see it instantly. Right? Yeah, probably because it's special. So, oh shit, probably in the GLSL mode we can find all of the keywords. So if we go into like Emacs-D, GLSL, do we even have ELPA, GLSL? And if I grep specifically for GL frag color, right, we will be able to find all of the special variables here. So the special variables are GL frag color, GL frag data, max varying, and so on and so forth. Maybe it highlights, oh, deprecated. Deprecated. Ha. That is interesting. But I mean, we're programming in a very old OpenGL. And yeah, that's interesting. Built-in list and so on and so forth. So apparently it is in fact deprecated, but don't tell me what to do, okay? I won't let some stupid mode for a stupid text editor to tell me what variables to use and what variables not to use. If I want to use this variable, I'm gonna use this variable, okay? Anyway, so I just don't know OpenGL that well. Anyway, Zosian.use it. I'm gonna use it. I'm gonna fucking use it. All right, it seems to be compiling, and what if I try to do that? Cool. All right, so we're setting the color of the quad to red. So what's interesting is that, where's the frag? Right. So GL vertex ID starts from 0, then goes to 1, 2, 3, and in binary this is 0, 0, 0, 1, 1, 0, 1, 1. Cool, right? So essentially, I'm actually writing that in the wrong shader. So here's the vertex shader. This is where we have to write all of that. Essentially, what we can do, we can take one bit, for example, we can allocate one bit to X and another bit to Y, right? And basically use them for all of this, right? So how to get this first bit? So we'll have to do something like GL vertex ID 1, right? We may not necessarily have to do that through bit operations. Does GLSL support even bit operations? I think it should. Yeah, I think it should support them. So we get this first bit, and essentially, if it's 0, that means the value for X has to be -1, and if it's 1, it has to be 1, right? So, and to achieve that, we need to take this entire value and multiply it by 2, right? We need to multiply it by 2, so it's basically we have values from 0 to 1. Right, we have values from 0 to 1, and we need to map those values to -1, 1. So that's essentially what we're doing. So first step in mapping 0, 1 to -1, -1 is to actually extend to something like this, right? We extend to 2. We extend to 2. And this is basically achieved by multiplying by 2. Then we can subtract 1. We can subtract 1, and this way, this thing is going to be mapped to -1, 1. So it's actually pretty straightforward. And this is going to be X, essentially. This is going to be X. All right. So this is only for X, and I wonder... So we can even try to do it like this. Oh my god. Alright, so this is X. For Y, we need to do the same, but with this bit, right? We need to do the same, but with this bit. So it's going to be the same thing, but we need to first shift to the right. We need to get rid of one bit, and only then try to extract that bit. See what I mean? Right. So, and we're doing all of that without any gray code, just to demonstrate how scuffed is going to look like. Yep. So does it compile? And too few arguments for vec4. Oh, okay. So then we need to fill up the rest of the arguments. So z is going to be 0, and w is going to be 0 as well. Cool. So this is going to be our stuff, and it doesn't even work. It doesn't even work. I wonder why. Maybe exactly because it's so scuffed. So we can try to see what it maps to, what kind of values it maps to. Right, so if we're using first bit as X, so that means this thing is going to be -1, right? It's going to be -1, and Y is going to be -1 as well, right? So then X is going to be 1, X is going to be 1, so X is going to be 1, 1, but Y is going to be -1. This is going to be 1, but Y is going to be -1. So as you can see, it's all over the place. It's all over the place. What if we swap them? W needs to be 1. Ah, okay, that's a good point. I completely forgot about that. So I was actually troubleshooting wrong. Yeah, there we go. Thank you so much. Thank you. This looks like some sort of like a flag. Yeah. And this is why like using like ID directly is not really feasible. You need to use the gray code. Right. So the gray code is actually super easy to achieve, if I remember correctly. To map one things to another, I wish it could give me just a formula, gray code formula. Hello Erhan Kurnaz 2000, happy new year to you too. Conversion of binary to gray code. It's actually a super simple formula. And I wish it just give me it, but it's not gonna give me. Of course, you cannot just write it like a normal human being. No, you have to give it this shit to me. It's something with Zor. Alright, it's something with Zor. Nth, yeah, I need the nth gray code. Yes. Yes. Something like this. Holy shit. Is that the right one? Okay, the formula for calculating nth gray code is this. I encoded it like this. Okay, I think for our case it's gonna be enough. So I'm gonna do it like this. It's gonna be gray. And instead of nths, we're gonna have GL vertex ID. There we go. And ID is completely incorrect. And instead of GL vertexes here, we're gonna use gray here. Hopefully that will work. And it didn't work because I forgot a semicolon at the end of this thing. And there we go. We generated the quad using gray code. We didn't have to set up any vertex buffer or anything like that. We're just generating the quad in the vertex shader without any bullshit. This is so beautiful. I really love it. I absolutely love it. Okay, so that's kind of cool. Not gonna lie. All right, so we have the data for the fragment shader and shit. So I don't think I need any of this shit anymore. So it's gonna be just literally like this. So very simple vertex shader. So we can go to the fragment shader. Here's the fragment shader, and now we need to move all of the math here. So in the fragment shader, what is the coordinates of the fragment shader? That's a good question. You know what? Before we go and implement all of the math, let's actually pass the points. Let's pass the points to the fragment shader. So you're going to do that through the uniforms. So the first step in working with uniforms, you have to get the location of the uniform. GL uniform. I think it's something like get uniform, right? Get uniform IV. And I think there's like a whole family of these functions. Uniforms, are you cosplaying now? Yes. I'm cosplaying now. I'm looking for a Japanese school uniform to cosplay a Japanese girl. Alright, so here it is. Is it AV? But I need another one. So I think there was like return a value of its uniform variable. I think it was something like location. GL get uniform location. Yes, I was right. It's a uniform location. I see. Yeah, that's what we need, chat. That's what we need. So let's actually get the uniform locations then. Alright, before we're gonna do all of this, so this is the program. We already linked the program. And it's gonna be P1 GL unit P1 U. I think like OpenGL people use like these kind of prefixes like UP1, and then you have UP2, right? And then you have something like UP3. Yeah. I'm just trying to put equals between them. It's not easy. It's not easy being Rin. So, and then we can set uniform set. I think it's just uniform like 2f. Yes. That's what we're doing here, chat. So yeah, we find the location, right, and we set the location to be something. The question is, what do we set it to? That's a good question. So right now it's kind of difficult to interact with this program, but not really. You know what? I think we can make a global variables, something like vec2f, p1, p2 and p3, and make them like this. They're global because maybe they don't have to be global. Actually, they don't have to be global because we're not using GLFW, we're using SDL, where you organize the event loop yourself, so you don't have to make any global stuff. The one thing that I don't like about GLFW is that you have to use like callbacks, but even with the callbacks you can actually pass your context, but it just makes everything kind of difficult. It would be better to, you know, organize the event loop yourself. I think it's just better generally, but I don't know. Okay, so here's the location, and the location is gonna be u p1, and what we're putting there is p1x and p1y. So yeah, essentially before trying to draw anything, we set the values of the uniforms. And this is gonna be p3. There we go. So here are the values, and then we need to implement like a simple interaction thingy that will let us modify the positions of these things. Cool. So let's try to compile all of that and see if it's gonna work. Okay, it seems to be working, and maybe I need to actually put them apart in different parts of the screen. So this one is going to be 100, 100, this one is going to be 200, 200, this one is going to be 300, 300. Cool. And before doing anything, you know what I want to try to do? I want to try to visualize them in the fragment shader, if you know what I mean. Visualize them in the fragment shader. We're gonna have some sort of like a radius, marker radius, and it's gonna be around, let's say 300. I think that should be enough. And essentially we're gonna just try different things. Can we define marker color as well? I think I can. So my marker color is gonna be literally this thing, right? Literally this thing. So essentially, I'm gonna take GL frag chord, right? So here's the GL frag chord, and I subtract P1, and I get the length of this entire thing. And if it's less than a marker radius, I'm gonna set the frag color to the marker color. Otherwise, I'm gonna set it to black. And what's interesting is that I just need to do that 3 times for each individual marker here. And if any of these things happen, that's what we're gonna have here. To be fair, like having a branching in the fragment shader, I heard is actually kind of bad. So maybe we could make it a mathematical operation of some sort, if you know what I mean. There's distance built in, but I already wrote this code. I don't want to rewrite my code, I'm sorry. Alright, so we're gonna put a marker color, otherwise we're gonna set this entire thing to be, actually not return a GL, a frag, I set frag color, right, frag color. Otherwise this thing is gonna be black, right, vec 40. Make sense? Does it make sense? I hope it makes sense. So that should actually draw these positions of P1, P2, and P3. Make sense? Make sense? Hopefully it makes sense. Alright, and it failed because we don't have a length. So no matching function for length error. Nice one. So that means we don't have glfrag chord. What is it called? Is it chord z? What is it called? I don't quite remember. I see. So it has to be like XY because yeah, it's four-dimensional. Yeah, I do remember that. There we go. Okay, and there we go. Here they are. So now we can draw all of these individual markers. How about that? How about that? That's actually pretty cool. I'm not gonna lie. I'm not gonna lie. And to be fair, like the coordinates are sort of inverted, so we'll have to take that into account when we take the mouse coordinates. So because I want to also control these things, right? I also want to be able to control these markers. And to be fair, I also need to share the radius of the marker, because I will need it to determine whether I clicked on the marker or not. Maybe because of that, the marker radius has to be a uniform as well. So let's actually make it uniform float, I think. Streamer showing thick curves. Okay. So now it's going to be marker radius. So this is a marker radius, and what we're going to do here this is not what I wanted actually. I wanted to do something like, there we go. And we're going to move it here. So let's turn it into a uniform. Okay. Marker radius. Marker radius. And I suppose it's initially going to be set to a marker radius. Marker radius is going to be just 1f, and it's going to be equal to 15, and maybe because of that we will be able to actually set it in runtime. Does it work? And if I change it somewhere here, make it 20. Cool. So now let's put it somewhere here. Define marker radius 20. Cool. Nice. So now when I'm handling events, I need to be able to check whether I'm actually clicking on any of these things. Oh boy, so it's gonna be kind of a pain in the ass, right? Because we have an array, and the easiest way to work with this thing would be okay, so we can actually have a pointer of some sort, right? So p selected. So this is going to be the indicator of what point is selected right now, and we're going to be trying to move all of this. So this is going to be case SDL mouse button down, right? And this is a break, and if event button is going to be equal SDL button left, right? And we need to check if the mouse position is actually close to any of these things here. All right, so mouse position, so this is how we calculate it. But the problem with this mouse position is that it's inverted. So Y goes down, but in our shaders, Y go up. How you remember all of this? I don't remember any of this. I just Google up things and copy paste from the Stack Overflow. All right, so X is okay, but Y has to be inverted. How can we invert the Y? Oh my God, I'm stupid. So I need to draw that a little bit. Because I was doing that for like 3 hours already, and I'm just tired. So that's why my brain doesn't really work well. So here's X, this is X, and this is Y. But we need to think with X, we don't even need to touch X, but we need to sort of revert it like this, right? So if we have this position, right? So essentially what you can do, right? So this is the value. and you need to find this thing. So you take your value and you take height and subtract y. Okay, that makes sense. That was easy. So what's funny is that like this is such a simple thing, but without visualization, I'm incapable of actually solving it. Alright, I just need to see that, right? My brain was incapable of visualizing that, alright? So, and what's that? It's gonna be screen height minus this, okay. That was embarrassing, but I mean, yeah. It's like, imagine that you need to do like 2 plus 5 and you start counting with fingers and just, what the fuck? Alright. Now, what is it gonna be like that? Because it gives you, yeah, I think that's that. All right, and the next thing, we need to be able to calculate the length of the vector, right? And we don't have such operation yet, so we have to do vec2 sub. So here is where is the place where we have all of this. So yeah, let's quickly do that. We don't even need the length, right? We don't even need the length, but maybe I'm gonna do it anyway. So vec2 length, vec2 a, and essentially it's gonna be ax. Come on, chat. Zozin, you don't need to take a square root. You can just compare squares. It's faster because you don't have to. Come on. Tell me that. So, and this thing has to return this thing. All right. So looks good to me. All right. Zodin. All right, so here we go. And if I take vec2 sub, right, I subtract what? P1 and mouse position, and then I do vec2 length, right? So here's the length, and if it's less than marker radius, right? If any of these things has happened, I essentially just do ps selected, becomes a pointer to p1, and we can copy paste this shit a couple of times. If we had an array of pointers, that would be a little bit easier, but this is just a demo, right? So this is just a throwaway code. It's not meant to be a production code. It doesn't have to be pretty, right? So we have something like this, so it becomes selected, right? In case of a SDL mouse button up, and especially if the button is the left one, right, because we only operate with the left buttons. I'm really sorry, left-handed people, but it is what it is. It's not a final product. It's actually not PS selected, it has to be P selected, right? It's a P selected, what P is currently selected. And we're gonna deselect it, like this. All right, so next thing, SDL mouse motion. So we're handling mouse motion. And in the mouse motion, we also need the position of the mouse. So I'm gonna grab it from here, right? I'm gonna grab it from here, put it here. And so, and if, and only if P selected, we're gonna modify this thing. So essentially we're gonna straight up set mouse position to the P selected. So it's pretty cool. Shaders, by the way, we're controlling this shit. First try. Look at that. This is so cool. This is so fucking cool, chat. Oh my god, it actually works. So, and yeah, we're controlling the attributes of the, like, uniforms of the in the Fragment chain. That's pretty cool. Am I an engine programmer now, chat? Am I an engine programmer? I think I am. I think I am. All right, so now we need to start drawing the curve, right? We need to start drawing the curve. Essentially, we're gonna do everything in a single fragment shader. We're gonna do everything in a single fragment shader. Also, let me actually make it a little bit brighter. I think these things are too... Yeah, now it's a little bit better. So you also have to, yeah, oh, god damn it, if you screw up the size of the window, oh shit. Fuck. Okay, so you have to, alright, we're gonna fix that a little bit later. So we can at least control the position of the markers and observe how the curve changes, but it can be fixed later. Don't worry about it, chat, don't worry about it. Anyway. So basically, first we try to render the markers, and if the fragment is not on the marker, only then we're trying to solve the quadratic equation. So the thing I'm gonna do, the thing I'm gonna try to do, chat, I'm gonna literally try to copy paste this entire code, right? I'm gonna try to copy paste this entire code into the fragment shader, and hopefully that will give me the solution. So we're gonna try to do it here. Alrighty, so we have this shit that we don't need, and I'm pretty sure I don't really need to make it constant or anything. So we have P1, P2, P3, and funny enough, we also have P0, right? We also have P0. So the threshold. Threshold. So let's define this threshold. Bézier curve threshold is going to be around like 10. Let's make it 10. And it's going to be something like this. Bézier curve threshold. And if this is true, right? If this entire stuff is true, that's a pretty thick condition, I'm not gonna lie. If this entire stuff is true, we're gonna set the color to, let's put it this way, Bézier curve color. Now I need to define this thing somewhere here. Define the color. So what's gonna be the color? Let's make it green, I suppose. I think green should be all right. 75, 0. Alpha is that one. Cool. So otherwise, it's going to be black. GL frag color. Hello, Penkyun. Happy New Year to you as well. So it's going to be vec4 0. Cool. So I think that's the thing we want to do here. Threshold is 10, so which will make the Bézier curve 10 pixels thick, hopefully. Let's try to compile this entire shit. Yep. Syntax error at 42. So what do we have here? Oh shit. Oh shit. I'm sorry. Sorry for what? Okay. Initialize the constant variables must be constant expression. Oh, okay, that's interesting. So maybe we don't have to make them constant then. Sure. It's sort of like a compile time evaluation thingy. Okay, let's not make them constant. I think it's a waste of time. The color if dex is... yeah, that's true. Okay, so... Thank you so much. By the way, are you trusted? Because you actually helped me a lot. I'm not sure if you trusted. Yeah, already trusted. Okay, I just don't remember if I trusted you. Because every time you say something, it's actually on point and it's actually related to the problems I'm having right now. It's amazing. Thank you so much. I really appreciate you. P0 is not declared, so we're gonna try to do it like this: vec2 p0 gl frag chord, right? And I think that's gonna be the thing. Fobs. I think we don't need to do that. Yeah, so it's gonna be just ubs. Okay. Frag initializer vector cannot be assigned. It's 22. Interesting. So it's actually two-dimensional, so it has to be something like this then. I think that's... Oh, no. By itself, this thing is... Okay, so this is the other way around, I think. Is that what it is? Okay. Holy shit! What the fuck? It's so cool! Look how smooth it... Oh my god! Oh, I see what's going on. It's actually like a ribbon. Oh my god, it's so fucking cool. It's not exactly what I expect. I didn't expect it to be... Holy shit, it's so cool. And look how smooth it is. Oh my fucking goodness. This is exactly... So, yeah, I kind of see what's going on here. So it's not exactly what I wanted, but it gives you like this ribbon thingy. Which is also cool, not gonna lie, but yeah. That's so fucking awesome. Holy shit. Even though it's not exactly what I wanted. And yeah. No need to interpolate anything. The problem is that the threshold distance is only in one dimension. Yep. Yep. Ribbon is even cooler. Yeah. Well, we can try to solve that, but I'm already happy with the results that we have here. I think it's already kind of cool. Yeah. Holy shit. Why do you see so many progress in the chat? I can show you. We implemented the Bézier curve purely in fragment shaders. So this is a purely fragment shaders Bézier curve that doesn't do any sampling, and it's actually doesn't require any interpolation. Like, it's infinitely smooth. It's infinitely smooth because of the math. We're using math magic to actually make it infinitely smooth, and it's fucking amazing. It's absolutely fucking amazing. This is so cool. It looks like a ribbon because, as 9-year-old said, it has a threshold in one dimension and not in the other, but overall, it's actually pretty fucking cool. Looks like kind of monkey to us, but can your textures do that? Yeah, exactly. So cool. I'm so glad I decided to do that anyway. I wasn't sure if like trying to do Bézier curve purely in fragment shader was even worth it. It's fucking worth it. The result is so cool. So this is one thing I want you to do, okay? This is one thing. Another thing, I want you to make it like fade away according to the threshold, right? Because how to say, can we do perfect subpixel anti-alias in the same shader? Yeah, this is what I was thinking about. Basically, we know the distance, like we know this threshold. We can use it to alter the color as the like Y goes away from the curve. So that's essentially what we can do. But here's the problem. Yeah, I need to commit everything. But I'm kind of afraid to commit that because I have stashed changes and I'm not sure how they're gonna affect everything. And also 2 lines of SDL plus 1 line of OpenGL. Yeah, so essentially now we have 2 programs, one like a CPU one and another one is a GPU one. And I need to clean up everything and separate everything. And I think the project should actually create 2 separate executables that you can actually check. And I think that's exactly what I'm going to try to do. Before I'm going to try to do that, maybe it makes sense to grab a thumbnail. This looks like a pretty cool thumbnail for the README, right? Because we're gonna, yeah, that looks cool. All right, so I'm gonna put it like this. So this one is gonna be CPU. We're gonna keep both of them. I want to keep both of the programs. So this is a CPU thumbnail, and we're also gonna have a GPU thumbnail. So the GPU thumbnail is somewhere down there. So here's the GPU one. I'm gonna copy paste it here, and 2021 thumbnail GPU. So in the README we have that, and so this is the CPU one. the GPU one. Cool. Holy shit, I'm so proud of myself. Oh my god, I didn't think I'm gonna pull that off. Like at first, the idea of using only fragment shader sounded insane and almost like outright impossible. But here it is. No interpolation. Sometimes it actually like goes away, but no interpolation, infinitely smooth. And the next challenge would be to do the same, but for 4 control points. For 4 control points, it's gonna be fucking cool. Because it's going to be super close to like actual real world applications that are out there, like, you know, vector editors and stuff, and it could be actually useful. And it will require cubic equation, but I think cubic equations are solvable in O of 1. All right, so so we deleted that. So let's commit everything here. All right, so implement degree 3 Bézier. Is that a terminology, by the way? Please add thickness slider. We can do that, but we can do that through the mouse wheel. Something like that. Result color smooth step. Yeah, probably. I'll look into that. First, I want to clean up everything. So implement degree 3 Bézier curve purely in fragment shaders. We're gonna push that right into the repo. Third order, second order, I don't know terminology, I'm not a mathematician, but yeah, you can check out the source code here. So since I already pushed everything, is it gonna look good? Bézier. Let's take a look at them. Okay, so this is the CPU one, this is the GPU one. So cool. God. So, and I have some changes here, which I'm not really sure if I want to add. So this is basically testing the math on CPU. Maybe it's not that important, like, because we already tested everything, so maybe it doesn't really matter, right? So we're gonna keep the CPU one original, and the GPU one is gonna be completely different. I think it does make sense. So I'm gonna discard everything from here. Okay, so let's go ahead and separate these two programs, right? So we're gonna have GPU.c, right? GPU.c. And I'm gonna start by doing the following thing. So GPU essentially requires this main, and I'm gonna put it here, and this is gonna be the CPU one. Right, this is gonna be the CPU one. Right. So now we have two source code files, CPU and GPU. I'm gonna go to the make file and I'm gonna build all of them. All CPU, GPU. Oh yeah, this one is a CPU and this one is a CPU. This is not how we do that. And then I can do something like this. GPU, cool. I might as well, I mean, I could use patterns in makefile, but I mean, it's not really required. Okay, so now I can remove that. Maybe it would also make sense to rename these shaders to GPU, because to sort of indicate that they are related to like GPU file, right? They're related to the GPU file Bézier, and yeah, it's gonna be something like this. GPU. There we go. Let's try to build everything. And okay, so you cannot build that because we have a shared code, right? We have a little bit of a shared code. Specifically, check SDL code. I'm not sure where I'm going to put all of that. Let's actually create something like common.h, where we're going to put all of the common parts, right? And in the CPU, we do have these common things. Specifically, one of the things we'll probably need is all of this checking. Oh my god, did I fuck it up? I think not. Okay, so this is definitely goes to the common. This checks also goes to the common, and maybe everything related to the vectors also goes to the common. Lerping, yeah, all of that goes to the common. Common H, there we go. Screen width, FPS, and all of the colors probably will go here as well. Why not? I don't see any problems here. And what's funny is that we also have a marker size. We can use marker size as the radius as well. I think it's actually kind of cool idea. All right. Okay, so what do we have here? Vec begin. And let's just include. Are you using GL 2.2? I think so. I'm not sure. I'm not really like good at OpenGL things, so I probably am using all of that. So yeah. And I don't really care what exactly I'm using. The only thing I need is just an access to the fragment shader. Alright, so if I can do fragment shaders and vertex shaders, I'm happy with that. So no matter what kind of version of OpenGL I'm using. So the only thing I need is just an access to a headway acceleration on the level of shaders. Right, at least for the thing I'm doing right now. Right, at least for the thing I'm doing right now. Okay, so here we probably need to include std.io. Right, so this is definitely will be needed. And another thing, SDL, so we also need to include that. Might as well actually take that from the CPU. So, you know what, I'm gonna just straight up take these things, put them here. And take these things and put them here. So it's gonna be the common stuff between these executables. But there's an option, you should use Vulkan. Yes, I should use Vulkan, I'm sorry. Okay. So compile shader file. Now we need to bring all of the OpenGL stuff that I put there. Where is it? Yeah, it's a compile shader file. So this is all OpenGL related things like linking and also marker radius. So I'm gonna bring everything here. And to be fair, we already have a marker radius. I can just use a marker size and basically reuse the same size between the programs. Okay, see slurp file. This is another thing that we'll probably need. And did I lose it? Did I lose it somehow? No, I didn't. So this is something that's could be useful between the programs. So I'm gonna put it into common. So there we go. All right. Now compilation of our nation. Okay. Marker size. Okay, cool. Both of the programs compile. Yay. That is cool. So now you can run CPU, and here is the CPU Bézier curves, right? That sample shit. And GPU ones works like that. So now you have two executables. To gain access to fragment shaders in Vulkan, you need to write about 1000 lines of code in my experience. Well, I mean, Old9 is kind of like memeing, so it's kind of a meme to, like, you know, at me and ask me these kind of things, so yeah, don't take it seriously. Zozin add multi-sampling. I mean, yeah, sure, I'm gonna do that. Why are you memeing? Okay, so git ignore. We don't need to ignore this thing. Is gonna be actually GPU and CPU. Do we need anything else? All right, so we have all of the fragments and shite, and yeah. Cool. Split CPU and GPU implementations. Cool. All right. So now all of that is available in the repo that you can check out here. How about that? Right. So now we have a separate executable for both of the implementations, and you can check everything there. Alrighty, so maybe I also want to update README. So here's a quick start. We can do a CPU and GPU. And maybe we can do something like this: CPU implementation, GPU implementation. Right, and we can just put them to their corresponding sections. And everything looks okay. Clean up README. So there's another problem that we still need to fix, and that problem is that, you know, dragging around doesn't work if the size is not correct. We have to take size into account somehow. Maybe we have to not update GL. No, we need to update GL viewport. But yeah, I will see how to do that. I'll see how to do that. That's so cool, so smooth. That's a smooth, thick and smooth, smooth line. All right, so sample PNGs, awesome. Yeah, it is awesome. So I do believe that READMEs, a proper README should contain like some sort of like a visual material, a screenshot of your program, so you can look at how it looks like, see how it looks like without compiling it yourself. Maybe you don't have an opportunity to compile it yourself, or maybe you don't wanna, you don't have time or anything, but you just want to quickly see how it looks like, and there you go. Here are some screenshots for you. So yeah, I think it's pretty convenient. So we already explored that. So explore how to render Bézier curves on the GPU using Fragment shaders. So I think, do we want to remove that? I want to remove that. So, and another thing for the GPU, so what we're gonna have here, dragging does not work if the window size is not correct. So this is one of the things that we have to acknowledge. We're probably gonna fix that a little bit later. But now we wanna make the threshold customizable. Right, we want to make the threshold customizable. How can we do that? So let's go to the Fragment shader, right? So here's the threshold, and just like marker radius, we can make it another uniform, right? So let's just call it Bézier curve threshold. It's going to be just a float, and it's going to just become this. Yep. And let's remove it from here. Let's go to the places where we use this Bézier curve, and quickly. What's up, TNK Hunk? Welcome to the stream. How are you fucking doing? Oh, this color doesn't have to be customizable. Yeah. Alrighty. So, hello, some random dev for 69. Welcome to the stream. So what we need to look for is Bézier curve threshold. Bézier curve threshold. There we go. Bézier curve threshold, and we also have some sort of a define here. Do we have anything like that? Yeah. Okay. So what we need to do here is float Bézier curve threshold. Initially it's going to be 1, right, or 10, and every time we set here, every time we draw a frame, we're gonna set it here. Bézier curve threshold. Bézier curve threshold. Cool. So let's see if we didn't fuck it up. GPU. So if we take a look at that, it still works. Cool. Now let's try to handle mouse wheel event. Mouse wheel. Right. So maybe I need to make another cup of tea. I'm kind of thinking about it. Because it's getting a little bit cold in here. What's the weather in Novosibirsk, by the way? Weather... minus 37. It's alright. It's alright, I would say. It's alright. Nuffly. What's up, Nuffly? Okay, I can see that you've been around for a while. I'm sorry I didn't notice you. Hello, Nafle. So we already handled mouse wheel in the CPU, so I can actually take the code from here. And yeah, so this is how it's gonna be done. So if the wheel is greater, we're gonna try to increase the Bézier curve threshold. In order to draw ellipse that way, I need to solve the equation with the same degree as 3-point Bézier, and 4-point Bézier is harder. Is that correct? I'm not a mathematician. I'm sorry, I don't know. Do I look like a mathematician? No, I don't know. Sorry, I'm just a Java enterprise developer. All right, so this is going to be a Bézier curve threshold. There we go, and we're going to increase it. Let's actually say that we're going to increase it by 1 for now, at least. All right, so we add, so we're gonna let it increase indefinitely. I think it's kind of okay to let it increase indefinitely, but when it comes to becoming smaller, I think it shouldn't be greater than 0, right? So it shouldn't be smaller than 0. All right, so let me see if it's gonna work now. So initially it's 10. All right, it's 10, and now I can control it with mouse. Holy shit. It looks so cool. Haha. That's some thick Bézier curve. I can actually increase it indefinitely, and then we could probably make it like 0. I wonder what's gonna happen if it's 0. Yeah, if it's 0, it's not visible, but yeah, now we control it. So we can try to increase the step. Bézier curve threshold step. Right now it's 1. We can try to make it something bigger. Step. Let's make it like 5. Yeah, this is GPU. It's done on GPU. So yeah, it's gonna be 5. It's gonna be. That's why it's so fast. At some point, like, it cannot solve somewhere here. When they line up, look at that. When they line up, it cannot solve the equation for some reason. It's kind of strange, but yeah, I wonder what's happening there. But apart from that, it's kind of cool. And not only is that some sort of like a non-situation. Yeah, look at that. So we'll need to inspect what is exactly going on at these particular points, but maybe a little bit later. So we can put a to-do here. So let's maybe go somewhere here at some combinations of P1, P2, P3. Nothing is drawn. There's a parabola which can go through 3 parallel points. There's no parabola which can go. That's a good point. Oh yeah, well, we can explore that a little bit later. Is it dependent on the thickness? I don't think so. I don't think it's dependent. But yep. So, and definitely when they are lined up. Yeah, so I can actually make it super small. Smoothness is off the roof. All right, so what we wanted to do, we also wanted to introduce the, you know, smoothing out or something, right? Somehow, not sure how, but we can try. So something like smooth step. People were suggesting smooth step at some point. Let me see. Smooth step. All right. So threshold -1 + 1x. Maybe, I don't remember what is a smooth step. It's like, oh, it's like a step function. I see. I think I know what it is. Yeah, it's a step function goes from 0 to 1 instantaneously. Smooth step is just like this. I see. Smooth step. GLSL. I just want to take a look at the documentation for this function, just what specifically it takes. Edge 0, edge 1, and so on and so forth. And it gives us this thing. First time viewing the stream, really cool stuff. Thank you. I'm actually doing all of that for the first time. I've never worked with Bézier curve. Well, I mean, it's for the second time. I started to do that yesterday. Yesterday I started to explore the Bézier curves, and we came up with a pretty simple thing that works on CPU, right? So this is like rendering and sampling is done on the CPU. And by going a little bit deeper into the math, we figured out how to do all of that purely in Fragment shaders on the GPU, making it infinitely smooth. That was super cool. I really enjoyed it. Oh, here, by the way, is all of the math. So I wonder, yeah, people were asking if I was asking if I need to export it. Let's actually export it to somewhere. And let's put it to programming. It's a home programming. Zozing Bézier. Oh shit. Oh, it's so dumb. What did it do? Oh fuck. And it's thinking about something. Like, what are you thinking about? Holy fuck, this is so bad. Where did it save it? I'm not even sure where it saved it. It's so bad. Okay, save it somewhere like here. In PNG, please. Okay. B Aura. Yeah, thank you so much. 20 megabytes, holy shit. Yeah. So it's something like scrap, and it's 8 megabytes, and I cannot even view that. And if I do fech, can I view that in fech? I think I can, but it's too fucking huge. Is it worth committing? I don't think it's worth committing. Nah, I don't think so. I'm not gonna do that. Alright. So what do we got? So this is that. Oh, yeah. We basically made the threshold customizable. GPU, make the threshold, remove the coordinate thingy. That one? I'm not gonna commit it anyway, so sorry. Make the threshold customizable with mouse wheel. Alright, I'm gonna push that right into the repo. Alright, let's try to figure out how to make the anti-aliasing, or at least make it smooth with colors and stuff like that. So we're probably gonna just modify the Y color, right? And because of that, Bézier curve can be something like this. We can make it vector 3, right? So this is a vector 3, and now what you do here is a vector 4, and then have alpha of 1, and we can multiply. We can actually put like a smooth step on this thing, right? We can put a smooth step on this thing. So it's gonna be the edge could be specifies the source value for interpolation. Do we really need smooth step? We could. Oh, smooth step is not linear interpolation, actually. Yeah, smooth step is not linear interpolation. It actually gives you like this thing, but maybe we could try with the linear interpolation first. Let's try linear interpolation. Maybe it will look okay. It's actually mix. Wait, you don't have lerp in GLSL? You literally have mix? Okay, makes sense. Why didn't they call it lerp? It makes so much sense to call it lerp, but okay. So what we're doing is just we are interpolating from 1 to 0, right? From 1 to 0, according to, I guess, something. It depends which threshold we pick. Okay, here's the problem, right? Here's the problem. So we don't know which of these things is actually the correct value, because we don't really care. But it's kind of important because it's going to be the final value, right? So that means one of them is the correct value. Which one? I need to reorganize this code, but I'm too lazy to do that. Okay. So we can take this value and essentially divide it by Bézier curve, right? So this is this value, and the second value is going to be this. And which one, like, sort of ends up being between 0 and 1 is the correct one, I suppose, right? So we can put them somewhere here. It could be float, and so it's a ratio, right? So it could be a ratio. It's going to be 1 and 2, right? And if something like this, it's really dumb, but I'm too lazy to come up with anything better. Sorry. And another thing is going to be R2, like this. You see what I mean? Okay, so, and did it even improve anything? I don't think it did anything. It's just the same thing. Huh. So what if I make the color literally like this? It feels like it didn't change anything. That's the problem. It feels like it didn't change anything. Yeah, it doesn't change anything. What the fuck? It feels like the alpha is the same. Is it because it has something to do with alpha? Okay, so I was hoping that it has something to do with alpha. We can try to change that like this. Let's try to do it like that. 0, 0, 1. So we're gonna affect the color directly. Now we're talking. Now we're talking. So this is what I was trying to achieve. But this is not particularly what I want. I actually wanted this to be alpha, right? I wanted this thing to be alpha. So if I put 75 here and then I copy paste this thing here. Oh, wait a second. I think for alpha you need to do OpenGL magic. Yeah, I think I remember that one. Yeah, for alpha, does anyone remember what kind of OpenGL magic you have to enable to have alpha blending of some sort? So yeah, I completely forgot about that. Enable, yeah. So it's like one of these things that you assume would be on by default, but it's not because of some historical reasons or whatnot. So yeah, OpenGL enable alpha blending or something. So blending, OpenGL, transparency, let's actually find out. And huge amount of text that no one cares about, literally no one. Okay, so GL blend funk. Okay, thank you, Surimans. Thank you. That's super cool. I know that you are a professional game developer and you know all of this stuff. Thank you. So GL blend funk. There's also GL enable blend. Who do I trust? Because this one looks easier. Let's actually give it a try. Never heard of DocsGL? Well, you're welcome. Typical Tsoding opens up a web page, reads 0, scrolls to looks. So what do you want from me? You need both? Oh, you need both. On a both. Okay, GPU.c. And where do I put that? Where do I put that? I guess I'm gonna put that like after we created the context. So we need to GL enable, and you know, 3 head copy pasting code from Stack Overflow, 5 head copy pasting code from the chat. I literally copy pasted 2 chunks of code from 2 different people. It's just into my code. That's a 5 head move. Who needs Stack Overflow when you have chat? Alright, so oh shit, that works so fucking well. Look at that. And if I, oh my god, this is a Craigasm, straight up. Oh shit, that is interesting. Look at that. It's sort of like, oh my god, you can sort of see it in 3D. It like overlaps itself in 3D, and it's almost impossible to see that without this kind of look at that. Like it's sort of like its projection becomes a window, and you can see the like a 3rd dimension of it of some sort. Holy shit. It's a ring. Oh fuck. Folding into itself. This is so interesting. It's sort of like gives you insight into like the math behind the scene, like what is going on there. So yeah, we see the another dimension. Holy shit, that's so cool. And I don't want to even fix all of these problems because they actually give you something interesting, like what's going on there. It's literally a ring of some sort, and it's a window. Huh. So what if what you're doing essentially, you are rotating a ring in a 3D space, and you basically project a small section of that ring on a 2D screen, and this is how you achieve the Bézier curve. Can you interpret Bézier curves like that? Like a 3-dimensional ring, but you project it on 2 dimensions to actually get the curve. This is just like I'm pulling that out of my ass. I don't know for sure. I'm not a mathematician, but it kind of feels like it. It could be. If you go deeper into the math, maybe this is something that's what you discover. So yeah, that's actually super interesting. Commit. Do you want me to commit that? I can commit that, sure. All right. So, and this is going to be a GPU. Enable cool gradient thingy. Did I spell it correctly? Yep. Thingies. Okay, so I spelled it correct. Thingy for enable cool gradient thingy. Cool. So let's push that right into the repo. Not sure how exactly cool it is, but it's interesting nonetheless. So maybe that means that we need to update the thumbnail. I think it means we need to update the thumbnail. So I'm gonna put it like that. It's gonna be something like this, and we're gonna also increase this stuff a little bit. That's looks like a pretty cool thumbnail. And there we go. Yep. I'm still pogging from the ring thing. Yeah, it's actually pretty pogging. Wait, where is my... Didn't I scrod it? Am I that Pepega? I think I'm Pepega. Alright, let's try to scrod it one more time. I think it didn't work. Right, so it was something like this. Then I put it like that. And then scrot minus S, and then just... That should give us the thumbnail. Yeah, there we go. Here's the thumbnail. That's what I'm talking about. And Bézier, let's copy paste it right here. Okay, so remove GPU and 2020, here it is. And we're gonna do something like this. Thumbnail GPU. Ah, this is not what I wanted. I wanted to GPU. There we go. So update GPU thumbnail. There we go. I'm gonna push that right into the repo. Whew. There's a lot of things that I would like to explore and probably fix, but I'm a bit tired. So some combinations, nothing is drawn. I'm gonna put these to-dos here. Maybe in the future we'll go back to them, or maybe someone else will discover them and fix them. So yeah, I think I explored everything I wanted. So another thing, okay, so another thing to explore would be to try to implement the math for 3 control points, and I think I'm gonna do that. Zoazin, okay, I'm gonna take a look. What is that? That's a good one. Yes, thank you for making it. It's literally me. Thank you so much. I really appreciate it. It's a special meme for me. Thank you. All right, that looks cool. Yeah, I need to add a to-do for the 4 control points math. So we're gonna put it somewhere here. There's a linear map between these spaces. You can embed the first and the second. If the first dim, I don't understand. I'm not a mathematician. I'm really sorry. That's the problem, right? I don't understand any of this, but I really appreciate lol at the end of it. So, which makes me feel better. Thank you so much. All right, explore math for 4 control points. Yeah. So because right now we have 3 of them. Nice meme. Yeah, it's actually pretty cool meme. Okay, so additional work for 4 control points. Let's push that right into the repo. Okay. Math for endpoints. Well, here's the thing. So according to what I saw so far, 3 control points require you to solve quadratic equation. 4 control points add additional recursive call that multiplies the whole thing by t, which will probably result in cubic equation. So adding more and more control points increases the degree of the equation. So yeah, at some point, I'm not even sure there is like a general solution for an equation of nth degree. So to do that for n point, you need like a general solution for like n degree equations, and I don't think it's a thing. Yeah, I think we have like general solution for up to 6 or something, and at some point they become extremely fucking complicated. So yeah, I don't think it's feasible to go anywhere beyond 4 points, because first of all, it's going to become like exponentially difficult, and second of all, in practice, nobody even uses more than 4 control points anyway. So yeah, going beyond 4 points is just like not worth it. And if you want Bézier curve that go beyond 4 points, you can actually take several 4-degree Bézier curves and just chain them together, and you can pretty much achieve the same result, right? So let's actually take a look. So we have, for example, like multiple control points for this Bézier curve, and that enables you with creating this spiral, right? Which is kind of cool, right? Which is kind of cool. You cannot achieve that with four control points, but you can achieve that with several Bézier curves with 4 control points. So yeah, you see what I mean? I so want to derive formula for cubic Bézier. Well, yeah, you can do that. Maybe we're gonna make another episode where we're gonna go into the cubic math. So it's gonna be the 3rd episode of the Bézier curve adventures. But we also need to develop a game. I mean, we'll see. We'll see. But in any case, I'm already tired, and I think we had enough fun for today. So it is time for me to go, boys and girls. It is time for me to go. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you tomorrow. Tomorrow, we're gonna do a game development. Well, we're supposed to do game development, but I haven't decided yet. I'm gonna try to play with the cubic math, and if the math is gonna turn out interesting, I might do another Bézier curve stream. We'll see, we'll see. So yeah, check out the source code of this project here. Check out it here. Check out our schedule for more information on different projects we're working on. And especially check out our WOTS channel, where we upload all of our streams. I I don't have an Instagram, sorry. Where we upload all of our streams, and this stream is going to be there, but tomorrow, right? We upload them on the next day. So I'm going to create a separate playlist for Bézier curve streams specifically. And also check out our Discord server for offline discussion with the community. Okay, and let's, I guess, rate somebody. Let's rate somebody. So, does anyone stream? Is anyone streaming anything interesting? Is anyone streaming anything like computer graphics or math? Something related to what we've been doing today? I actually kind of like today's stream more than I liked yesterday, because we like looked deeper into the essence of Bézier curves and discovered something interesting. It's kind of cool. Pailada is streaming, so is he streaming programming? Maybe. Games and shit. He's streaming deeper into the. Okay, Donho is streaming. Is he streaming game development? PRC Keck game engine. All right, let's actually rate him. So let's do rate. Donho. He rated us last time, so I think it makes sense to actually rate him back. All right, so get ready for the raid, boys and girls. Get ready for the raid, and I see you all tomorrow. Love you.